Hey everybody, we are live. We still have a couple minutes here, but I thought I'd go ahead and get on, make sure everything is working well. So we're going to get started here in just a couple of minutes, and we will start going through and get you going here. We also have on Discord in the physics channel, we have Brianna, the TA. She's going to answer a ton of questions for you. So we'll look forward to having her do that. And that will be awesome. So anyway, I think that is it. We're also going to use Pear Deck tonight. Pear Deck is the way to go in terms of just helping you understand things. So you'll kind of see that as it goes through. So hopefully that works out really well. So I think that should be the way to go. I'm going to, here we go. And I'm going to share this. We're going to have a special guest tonight, and they're going to come in and talk to you just a little bit. So hopefully that will be super awesome, and you'll like that. We have plenty of people signed up tonight, so when you ask questions, just be super patient. Hopefully that will help out a little bit, but we will just keep going. So we've got 5 o'clock right on the button. What we would love for you to do is go ahead, and if you join the Pear Deck that you see here, so there is this really cool way of allowing you to go through and be able to really kind of be active in this and ask questions and do some things like that. So that should be super helpful. And we're going to give it just another 30 seconds or so, and then we're going to get going. We do have 5 hours tonight. We're going to do all kinds of stuff, and hopefully we will get you super duper ready for tomorrow. And other than that, I think that's it. So I am going to start the Pear Deck. If as you all come in a little bit later, I will put the Pear Deck code. You'll see the code is up here in the corner. And all you've got to do is just come in and kick on that Pear Deck. All right, here we go. So I will give you a heads up. So this stream is being recorded and might appear on the Fiveable website, YouTube, or other public channels. If you ask a question, your name might appear on the screen, or we might read your name. So just please know that as we go through. Please change your name if you want to avoid this. As always, at Think Fiveable, give us a shout out, kind of let us know what you think. And you can do that on Twitter, on Instagram. You can do that on YouTube. Please also join our Discord channel, and you can just jump on and do that. Ask questions. We have some awesome things going on there, and you will notice that Brianna is there, and she is fantastic, and she is answering all kinds of questions. So we'll get you on that. So from 5 to 5:55, we're going to do energy. And then from 6 to 6:55, we're going to do momentum, all things momentum. We're going to look at simple harmonic motion from 7 to 7:55. From 8 to 8:55, I'm going to give you as many free response question tips and tricks. And from 9 to 10, that should say 9 to 10, that's my fault. Multiple choice tips and tricks with a Gimkit challenge. So we'll do all those things. Let's talk about the exam just a little bit, just to make sure you kind of know what is coming up tomorrow. So if you are taking the test tomorrow, good luck tomorrow. It will be super fun. You'll probably think, oh my goodness, and then you will be set. So make sure you take your time on the exam, but let's talk about the exam just a little bit. If you're taking it either tomorrow or in May, at the end of May, on the 24th of May, then there's some things that you need to know. First off, multiple choice. There are 50 questions, and that sounds like a lot. It is, but you have an entire hour and 30 minutes to do this. It is 50% of your exam score. And the questions here are either what we call discrete questions or question sets. So they're standalone questions, or they're ones that there are a couple of questions for maybe a picture or a graph or a reading or something that you have to do. The other part of the multiple choice is 5 multi-select questions where 2 options are correct. I will tell you this, when you do those 5, those you have to get both answers correct to get credit for that question. So make sure you do those first 45, do them well, answer the last 5, make sure that you choose 2 options. So that is super important. The second part of the exam is another hour and 30 minutes. You will have 5 questions. And in these questions, you will write, and you're going to write a whole bunch. There's not a lot of math on this in terms of solving for just a single answer. So you're going to see things like it's going to ask you to go in and explain or describe physics. There's not a lot where you're going to solve for the speed of something or where you're going to do things like that. So kind of just watch and you'll see kind of how that happens. That is experimental design. There's 1 question. There's a qualitative, quantitative translation. That's 1 question. There's a paragraph length response or a paragraph argument. That is 1 question. And then there are 2 short answer questions. So when we do our free response section tonight in hour 4, we will go through a little bit more about that. So what do you need? You absolutely positively need a calculator. And you can use any calculator that you really darn well want to. That means that you can use a graphing calculator. You can use a really inexpensive calculator. The best calculator to use probably is just a 4-function calculator that also will allow you to do sine, cosine, and tangent. So make sure that you have one of those. It just can't have a keyboard on it where you can type. So obviously you can't use an iPad or anything like that. Pencil. Make sure that you use a regular pencil. They do not want you to use a mechanical pencil. Sometimes those mechanical pencils don't make a mark that gets picked up by the scanning machine. So this is on Scantron. Both of the May exams are on Scantron, which means that you have to bubble. A ruler, yes, you may use one. In fact, make sure that you have a ruler. If your teacher is not providing a ruler, you need to make sure you get your own ruler and take it to the exam tomorrow. Or a straight edge, something that you can use so you draw straight lines. Free body diagrams have straight lines on them. If they look curved, then we grade them as curved. So I'm going to go back and introduce myself for just a second now that we've got a lot more people in. My name is Christian Horner. I am I'm an AP Physics reader and I'm a table leader. And what that means is, hi there guys. What that means is I get to read all of your exams every single year. And so I sit down with about 500 of my wonderful physics friends from all over the country, and we read your exams. So each person will probably look at in between 5,000 and 10,000 of the same question for all the students in that group. And so when we see things, we can tell you one of the things that a lot of students forget to do is they absolutely positively forget to bring a ruler. So you'll want to make sure that you absolutely bring a ruler. And that way you can do your free body diagrams and your best fit lines on graphs. So what I'm going to do right now is I'm going to welcome Amanda. Amanda is the CEO of Fiveable, and she's going to come in and talk to you a little bit and get you pumped up for the AP Physics 1 exam. So
what's up, AP Physics 1 students? I'm so excited. I'm Amanda. I'm the CEO of Fiveable, co-founded Fiveable 3 years ago, and I'm coming to you live from the Fiveable house in Milwaukee, where we're just like helping a lot of students kind of running around, trying to answer as many questions as we can. It's been really fun. So I have a couple of things I wanted to let you know about. One, make sure you post any content related or FRQ related questions in the discussion threads below. So even though Christian will be going through all the content, you can get your questions asked and answered in the discussion threads. 2, if you have any tech issues or questions about the stream or anything like that, just chat us in the box below, in the little chat bot where my face is with the little mustache. We'll make sure to be answering those questions too, but it's different people who are answering those. So make sure the content goes in the discussion threads and tech goes in the chat. And lastly, we did this last year, and I'm really excited about this. At any point tonight, while you're in your cram, or if you're watching this in a watch party, post on social media about your cram experience. You can post on Twitter, on Instagram, or on TikTok. It could be anything about what it's like to be in the 5-hour stream, something about the physics content itself, show your study space, call out College Board for their nonsense, anything like that. Something that makes other AP students just be like, that is 100% accurate about what this experience feels like. Tag us at use the hashtag YesWeCram and with Fiveable, and tag us at Think Fiveable. We're going to be giving away $100 every night between now and the end of AP exams to the best submission of that day. So what does it mean to be the best? Get a lot of likes on it? Is it a fan favorite? Are we just like really impressed by like your creativity and feel like it really talks about the experience? And include Fiveable in some way, even just in the caption, or if the content itself is about Fiveable. So get your submissions in. This is a fun way to take a little bit of a break. 5 hours is a long time. Post something out there. We're going to be retweeting and sharing all these different posts, so we'll amplify you. And $100 is going to pay for someone's AP exam. So get your submissions in. I can't wait to see them. I'm going to be giggling all night watching them while you guys are learning physics. So just remember tomorrow on your test, take a deep breath. You totally got this. I know it's super stressful. I know there's a lot going on. It's been a wild year. Maybe you didn't get through all the content in your class. It's okay. You're going to be fine. You're here. You're in great hands with Christian. And no matter what happens tomorrow, we are so proud of you. And you're still part of this family. So we're wishing you all the best luck in the world. And you got this. So Christian, I'm going to pass it back to you. Good luck tonight. And I'll see you guys later.
All right. So now I think I've got my sound back on. So thank you so much. See, Amanda takes care of everything. She's awesome. And we should be back. I want to make sure. Yep. Looks like we're good. All right. Cool. You guys rock. All right. Here we go. We were talking about rulers. So make sure that you have a ruler for this exam because you're going to draw free body diagrams. You're going to have best fit lines, all kinds of cool things like that. And if they're not straight, we can't give you credit. So you want to do that for sure. All right, this is where you guys come in. This is what I would love for you to do. I want you to go in, and this is the top half of the equation sheet. So this is the actual equation sheet that you will see in your test book tomorrow if you're taking the test tomorrow. And what I want you to do in this is I want you to cross off. So literally, that's what you're going to do. You're going to cross off the parts that you are not going to use tomorrow. And yes, you will not use some parts tomorrow because they got rid of some sections. And we love the fact that they got rid of these sections because that made this so much easier of a test. So right now, I see a lot of people have marked off the exact sections that you don't need. That makes me smile. That makes me super happy. I am so thrilled that you guys know which sections you should not pay any attention to. So here we go. I'm just going to show you one of those responses. And this young person has been with us since day one. They are doing an awesome job. They've been through and done a lot of free response. They also have done all kinds of some other things too. So excellent job. So beautiful. You guys are awesome. I'm looking and everybody is crossing off the section you don't need. When you get your test tomorrow, you need to do that. Cross those off. You do not need those two sections. Those sections are not going to be covered on the exam. So beautiful job. All right, let's move on. Here we go. Don't forget, there is a math-based help section on the exam. And this math-based help section has everything from the area of a triangle and a rectangle to the area of a circle, as well as the circumference, which you absolutely positively will use tomorrow. So please, please, please make sure that you use it tomorrow, especially when you're doing circular motion or rotational motion, one of the two. All right, that's a great thing. Now, here's what we're going to do next. I want you to cross off anything that you're pretty sure you're not going to use tomorrow on this part of the exam, okay? So this is the one, this part of the equation sheet gives you all the constants. It gives you like gravity is 9.8 meters per second squared. So you will see that right here, that 9.8 meters per second squared, you can use 10. Please use 10. It makes your life easier. And when I have to grade your test, it makes it easier on me. When the people around me grade your test, then it makes it easier on them. So hopefully, you realize that 10 is the way to go. Now I'm noticing people are crossing stuff off, and so I'll show you kind of what they're crossing off. You do not need to know all these little things about the masses and the charges of things. There are some things up here on the top that you don't need to know that are about electricity. And so the ones that we really just need are big G and little g. Those are the two things that are super important. Some of the unit symbols, you're going to notice they're here too. And those are all super important. So excellent job. Way to go through and do that. Looks like we've got a lot of people on here doing this. So no electricity, no magnetism, no waves, and no electrostatics. So those are some other things that you 100% do not need to worry about. Good job. All right. So this is the next part of the equation sheet that you need to make sure you read. The prefixes and the conventions are super useful. The prefixes are on the left side. So you'll notice that if I can't remember what milli is because I am super tired, I'm just trying to get through the exam, you will see right here it says milli. Milli is 10 to the negative third. Milli is 10 to the negative third. So now I know what that is. Kilo, 10 to the third. You probably won't need these trig functions. They probably should take this out at some point, but they do this just in case you have a calculator that does not have sine, cosine, and tangent on it. They will try to stick to these values for angles, so you probably won't see any other values for angles. The other thing that I want you to really pay attention to is the following convention. So these are things that you can assume are true unless they tell you otherwise. Air resistance is negligible. Don't worry about air resistance unless it tells you to worry about air resistance. The other thing is it deals with work. They define positive work for this test is work done on a system, not by, but on a system. So please make sure that you see that, okay? Because chemistry can be different. And so if you're taking both AP Chem and AP Physics, more power to you. But if you're doing that, then that is awesome. But please watch out because work done on a system is positive. Let's talk about work, energy, and power now. So this is the beginning of the first section, which is energy. And we got our good friend here, got Doc on here, is 1.2 gigawatts of something or another. So that'd be power, right? On the equation sheet, make sure you know where all these equations are because they're somewhat scattered on the AP Physics 1 equation sheet. If you want to and you have time, you can go in at the beginning of the exam, go to your equation sheet and put E next to each one of these so that you remember that they are all different things that deal with energy. So those are super important. So we've got potential energy due to gravity. We also have potential energy due to gravity. But notice this is the change in potential energy. This is also the potential energy due to gravity, but this one is different in that it is between two masses that could be orbiting each other, okay? We also have spring energy, kinetic energy, and rotational kinetic energy. Make sure you know the difference between those. Delta E, remember that is change in energy. That's the same thing as work. That is force parallel to distance, or FD cosine of the angle. And then our last one here is just power. We've got all those things again, so you can kind of see our units. Notice that all the units here except for power are joules. So work is the change in energy. So therefore, we have to look at it as a joule, okay? So everything else on here, you should know and you have seen before. One that you might not have seen is you can use for kinetic energy the momentum squared divided by 2 times the mass. So that also comes out. And that's because if you multiply m times v, what do you get? Yes, you're right. You do get momentum. And so that's what we've done here. Taking a look at the next slide, this is a few more pretty important equations. One of them is the work done by friction. Friction does work. This is also energy that is lost to friction. You're going to notice that it also says here given, and that means that this is this given on the equation sheet. No, this is not given on the equation sheet. So watch out. This equation is not given on the equation sheet. Neither is the conservation of energy. Now, power in terms of force and velocity, that one is on there. So be really careful. You can find that one there, okay? But other than that, that is it. I think the big one that people forget about is the work done by friction. So we'll talk about it a little bit more here in a second. Important graphs, force versus displacement. Whenever you see an F versus X, or you might even see an F versus D, that is a graph that is showing you work. So if I multiply my force times my distance, or I find the area under the curve here, that would be work. So please, please, please watch out for that. All right, good. Some other concepts that are super important for you to remember. No work is done if a force is perpendicular to an object. So you got to kind of think about it that way. You have to be pushing it in the same direction or stopping it in the opposite direction. Using your energy equations, if you are asked for velocity in terms of position or position in terms of velocity. So we have a lot of different equations there, and they are equivalent. So here we have work is equal to the force times the position, and it's parallel. Here, same thing, okay? So, but just watch out for these. Cosine does a good job of finding the parallel component for you. So as long as you use these equations, you should be set. So that's enough about equations. Let's talk about something that's a little more important. Remember, work is the transfer of energy from one form to the other. So this is kind of like the money of physics. Whenever we transfer work or transfer energy, that's the money. So, you know, if I want to buy something and I want to build a house, then I have to use money. That's kind of my currency going through. If I want to do work, so for example, I want to lift a board up in the air in order to build that house, the money there now is energy. If work is positive, so there's a gain in energy. So for example, if I lift something up above my head, then that is positive work done on the object. So always focus on the object. If work is negative, then it's lost energy. So if I drop a bowling ball, then it loses potential energy, okay? Yeah, it gains kinetic energy, but we're looking at what I'm doing. So if I'm setting something down, that's essentially what we're doing. All right, nice, nice, nice. A force does work if it acts on another object. You can think of positive work if the force and direction are less than 90 degrees. It's negative if it's more than 90 degrees up to 180. And if you have it perpendicular, there's no work done there at all. So you're going to see that just a little bit. I think in the end, you have to be really careful. The work done on an object is positive if your potential energy increases. The work done by a force is negative. So if I am using force to lift something, I am doing negative work, but the object I'm lifting is gaining energy, and that's positive work. So you can really think of potential energy increases as if you're forcing an object to do something. For example, objects want to fall down. Think about a bowling ball. If I lift it up in the air, it does not want to do that. It wants to fall. Springs, they don't like to be stretched or compressed. And when you do that to them, that's opposite of what they want. So you're increasing energy anytime you do something and it makes that thing unhappy. So making a spring unhappy, making an object unhappy when you have it and you move it away from the earth, okay? Here's a good example. If I lift a book from a low shelf to a high shelf, I do positive work because the force I exert up is in the same direction as displacement. My potential energy decreases, but the book's potential energy increases. On the other hand, the force due to gravity did negative work because the force due to gravity down was opposite, and the gravitational potential energy did increase. The big concept here we're thinking about is we always want to use energy whenever we're given a position and asked for a velocity, or given a velocity and asked for a position. So that even happens when you have a circular orbit. And one thing that you need to remember is when you have an object in uniform circular motion and the speed is not changing, there's no work done because you're not changing its kinetic energy at all. So remember that. That's super important. All right, finally, something that you can do. Okay, here we go. I have a block. That block is on an incline. And you're going to notice that on that incline, that block is just kind of sitting here. They want to know if the incline is frictionless, how fast is that block moving at point B? So we're starting at point A. The block starts here. It moves down to the bottom. And we want to know how fast is that thing moving when it gets down to the bottom. So we want to know how fast is it moving when it gets down to the bottom. All right, so I'm going to give you about 4 minutes, and I want you to try to figure this out. Type your work as you go. So one of the things that you'll want to remember on the AP Physics 1 exam is you really, 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 really want to make sure that you show all of your work, no matter how trivial it seems. We cannot read your mind. So when you're doing these, if you don't show work, then we don't know where you really started. That's tough. That makes it really, really difficult. So I'm going to kind of look at your responses. I'm able to see what you've typed. I will not show anybody what you have typed, I promise. I will show some example responses that you guys show, but your name will not be associated. That's the best thing about Pear Deck. So I'm seeing a lot of great responses here. You guys are going in and you're showing me exactly what I want to see. And that is always start with your energy. Okay, so this one definitely, remember, we're on energy. So you want to do this using energy. So think about the types of energy that it has at the beginning and the type of energy that it has at the end. And I think if you do that, that will make this one a lot easier to do. Oh, beautiful, beautiful responses. You folks are doing awesome. I love it. So we're just trying to figure out, and you can either use the typing tool. So you'll notice that there is a tool there to type with. So if you want to use the typing tool, you can do that. If you need to abbreviate anything like square root, you can use SQRT. That works out really well. But I'm already starting to see some awesome answers here. So I've got people with the right answer. Beautiful. Very, very, very nice. Notice that you can change the size of your pen if you're drawing. So if you're on an iPad or you're on a tablet of some sort, or you have a computer that's a 2-in-1 and you're able to write on the screen, then that works really, really well. I love it. So beautiful job so far. Seeing a lot of great things here. The few people drawing free body diagrams. You really don't have to draw a free body diagram for this. Okay, so I think we're really at the point now where we have a lot of great correct answers, and I want to show you some of these. And you can actually solve for a number here. So you won't do that all the time, but you probably are going to do more things like just solving for maybe what a letter is, and it'll say derive an equation. So we'll talk about that later too. All right, just some beautiful answers here. It doesn't have to be pretty, but you do have to make sure you go through and show your work. Beautiful job. You guys are on it. You guys are all going to pass this test with no problem. Oh, beautiful job. Great, great, great. Excellent. All right, here we go. Let's show some of these responses so you can see what people are doing. All right, here we go. So this first person, they started with conservation of energy. They then solved for V, plugged their numbers in, and got 17.32. So excellent job. I love it. That is beautiful. So let's go ahead and take a look at the next person here. If we can, we'll get it to scroll down a little bit. But that is the right answer, 17.32. Awesome. And so let's see if we can see another one here. So here's one that somebody typed exactly the same thing. And you're going to notice that they also have that same answer. So on the next screen here, I have, well, you know what? I'm going to back up one. Yeah. So on this screen, I went through and did it based on kind of what we'd love to see when we sit down to grade your exams. You want to show conservation of energy. So for this one, you can either start with UG is equal to K, or you could start with MGH or MG delta Y is equal to 1/2 mv squared. Notice that we never gave you the mass. And so if they don't give you a variable, but you see it in the equation that you're writing out, 99% of the time, that means that that will be crossed off. So I think the flipping physics, gentlemen, so if you really want a good website to go to kind of brush up a little bit, if you go to flippingphysics.com and go to the review for AP Physics 1, he will talk about everybody brought mass to the party. So you'll notice that there's mass on both sides. So everybody brought mass to the party, so we don't need it. So we can cross it off. So we don't have to worry about anybody else bringing it. At that point, we've just done the velocity is equal to the square root of 2gh because we had to multiply both sides by 2 and then take the square root of both sides, and we end up with that 17.3. So now we know the speed if we were going 0 at the top, and now we know how fast we're going at the bottom. So that's letter B. Awesome job. Let's do this. So now if the incline has a coefficient of friction of 0.11, what would be the new speed at point B? So we're still dropping it 15 meters. It's still going down that incline, and it still gets to point B. But they want to know, what is the speed? What is the speed at point B? Somebody in Discord just went in and put in a link to the AP Physics 1 review and exam solutions from Flipping Physics. Thank you so much, Hoofed Wheel. That's awesome. I'm so glad you did that. Thank you for helping out. So you did a really good job with that. Thank you for doing that. All right, I am seeing people starting to do this question, and that is awesome. I love it. And you got to think about what we just did. So remember, we went from potential energy to kinetic energy. If we add friction, remember we said that if there's friction, then there is work done. And remember, work is the force times the distance. So the big question I think you have to ask is, where is the distance for friction to act? So is that the 15 meters or is that the 25 meters? So that's kind of the harder part. But you definitely want to start with potential energy due to gravity, and then recognize that in the end, you're going to have kinetic energy at the bottom, but you're not going to have as much, because remember, friction is going to remove some of that kinetic energy as heat. And so you've got to figure a way to get that out. So one of the things that we tell students to do is think about money in, money out. Okay, I have to have the same amount of money, but if I start with $20, okay, and I go to the bank and I do something, okay, or let's say I go to the store, I go in to buy, I don't know, let's say a Kickstart, like a Mountain Dew Kickstart. I go in, I give them $20. They give me back $15 and a Kickstart. So I don't have as much money as what I started with. So where did that extra money go? Well, they kept that money, but they gave me something in return. So I got that Kickstart. When the block starts at A, that's like your $20. I want to know how much money am I going to have at the bottom for speed. And so at the bottom, for the speed of the block, it's not going to be as high. Why is it? Because some of that money goes into this friction. And that's my kickstart that I get out. So that's that heat that comes out. So I've got to think about a way to do that. So it looks like some of you are starting to get it, and you're doing pretty well. And so I'm seeing a lot of good things. I'm seeing some answers here too. This one is a little bit more difficult, for sure. For sure, for sure. It is a little bit more difficult because, yeah, excellent. We've got to go in and we've got to find out. Yeah, there we go. Some good answers here. Beautiful job. Seeing some wonderful things that you guys are doing. Yeah, good. So remember, we're going to have on our left side potential energy due to gravity, and on our right side kinetic energy plus the work done by friction. But remember, that's negative. Okay, so those should add up to W, should add up to your potential energy on the other side. Wow, awesome job. Beautiful job. Seeing some good answers here. Really good. Giving you just a little bit more time. We've got about 230 people right now on the on Pear Deck. So that is fantastic to see. You guys are all working super hard. Do the same thing tomorrow. You're going to be set. Boy, you guys are doing great. I love it. Excellent. Seeing some awesome answers. I am giving you a little bit more time for this one. You guys are doing fantastic. I love it. I love it. I love it. Awesome, awesome, awesome. And we are going to show you the answer. Remember, you still have access to the stream as well as the resources. So if you don't get this one, it's cool. You'll be able to go back. You know, make sure you get some good rest tonight. So if you're on the East Coast, we get done about 10. If you are in the Central Time Zone, remember, we get done about 9. So you might have a little bit more time to go through and do some things. So awesome. Wow, this is great. You guys are just knocking this one out of the park. All right, let's take a look. Let's take a look at the answer. Let's see what we've got so far, okay? So this one is a little bit more complicated, and it's more complicated because we have to worry now about that friction. So here's the force of friction times that distance. But you're going to notice we've got to do some things. One of those things that we have to do for this problem is we need to figure out, we've got to figure out what is the force down the hill. And then what else is that we need to know is we need to know what is the normal force. So one of the things that we have to think about is how do we draw a free body diagram for this? And so when we draw a free body diagram for this, we just have to be really super careful. So one thing I want to do is I'm going to open up a new tab here, and I just want to draw this free body diagram really quick because I think this is super important. Now, it's not going to be the best free body diagram in the world, but there's my incline. Here is my box. So I'm going to have one arrow that is going to point straight down. And we know that that arrow is going to be mg. I've got another one up that is perpendicular to the surface. And then I have my friction that is going in this direction. There's not another arrow that goes down the other way. Okay, so you've got to be really careful that you see that. So I've got one arrow this way, one going this way, and one going down. So this would be your free body diagram. You need to label everything for this one. So this would be your normal force. So you could do F, with your N down on the bottom. This one would be the force of friction. So you can just use little f. And then this is mg, or you could do fg. But on top of these, we also need to make sure that we draw the components. So one of them is perpendicular to the surface. The other one is parallel. And if we have, so right here, we have an angle. So this angle would be theta. This angle is also theta. And I always know that if this angle is with the horizontal, this one, okay, if I just take this and just rotate it, you'll see it's the same thing. I always remember it's right next to the dot. So there's usually a dot here that you would draw. So now I can go in and I can label what these different sides are. This side is the adjacent side, so it's mg cosine of the angle. And I'm going to put Q in for the angle just to make it easy. And then this one is mg sine of the angle. So if I want to say the force of friction is equal to mu times Fn, I can't use Fn. I've got to use mg cosine of the angle. So if we go back, you'll see that mg cosine of the angle, that is Fn. So that's where that came from. Mu is just the coefficient of friction. And we now need to take, and remember, we've got to multiply that times the distance. And our distance is not 15. That's how far we fall. So that's great for energy, but it's not great for what we're doing in terms of friction. That's actually 25 meters. So when we do our final equation looking for that speed, notice it's 2 times gravity. Remember, we want to use 10, makes it so much easier, times the height. And the height is 15 meters. Minus, now we've got mu, okay, times, well, we've got 2 times mu. So 2 times mu times gravity times that distance, 25, times the cosine of the angle. And that gives us 16 meters per second. So awesome job. For those of you that got 16, congratulations. If you didn't, that is okay. You don't have to worry about it, all right? Last thing that we're going to do on this problem is I want you to go through and I want you to figure out how far does this now travel along X until it gets to letter C. So far we've found out that it's going to start at A, go down to B. If there's no friction, we know that it has a high speed. If there is friction, like in this one, we know that the speed at B is only 16. And then if it's going 16 here, it's going 0 here. So now what we're going to do is say, well, how far did it travel? So you really don't have to do anything in terms of figuring anything out on the incline. Just start with your speed here. Figure out that, and remember your speed here is 0. So we had to lose energy due to work. And remember that work is friction. So now we're looking for how far did it travel. Remember your beginning speed here is 16. Obviously your ending speed has got to be 0. So go ahead, take your time. We'll give you a little bit of time to answer this one. So I'm going to kind of watch, see what you're doing, and then we'll take a look at your answers and see how well you did. Guys are doing fantastic here. We still got about 10 minutes left in this first session, so hopefully it's flying by for you. You're super busy and you're doing a great job. So I love to see that. Trying to figure out what is the distance. Oh, excellent job. I've got a great answer here. Excellent, excellent. I love it. So I'm going to show some of your answers. Your name will not be attached, so don't worry about your name. And there are different ways to do this, I think. So I'm seeing some beautiful ways to do it. Excellent. Very nice. Some of you are writing down what you know, and that's great. That's what we want. So do the best you can. Remember, a lot of things you can solve with energy, and this is one of those things. So if you use energy to do this, it is fantastic. Excellent job. Always remember to write an equation first, because that helps us understand what process you're using. So usually when we do these, you can start with F equals ma, or you can do conservation energy, or you can go through and do conservation of momentum. Excellent job. I love it. Seeing some beautiful things here in terms of answers. Guys are super busy. I love it. Getting those brains going. Guys are doing fantastic. We will take a 5-minute hard break. We want you to get up, move around, do some things like that here in a little while. There's even a timer so that you can kind of watch. No pun intended. Ah, beautiful job. Excellent. I know some of you are patient. Thank you for being so patient while others kind of work their way through this. We want to give everybody a little bit of time. Fantastic. You're all starting so well. I love it. We'll get to momentum and we'll do some things with it next. It's looking really good here. All right, I want to show you just a few responses, not very many. We'll see if this comes up. Sometimes it takes a little while. Just because, there we go. Whoops. So I think I've maxed out what I can do in terms of showing people's responses, and that's okay. Let me show you what the answer is here. So we'll give it a second to flip to the next one. All right, here we go. Got to get it unstuck. Oh, we're going to back it up just a couple here. Sometimes it wants to get a little bit confused, so we're going to back it up a couple. All right, here we go. So here's our answer. Oh, it jumped forward again. Sorry about that. Happens when we have lots of people. And there we go. Okay, beautiful. We know that we're starting with kinetic energy at the very bottom. So right here, we have kinetic energy. And then we're going to lose energy in terms of work. And remember, we said that that work is friction, and that's it. So we're going to go from there to the next part. 1/2 mv squared is what we have here. We know that we get rid of that energy, and then it doesn't have any energy at C. It's all dissipated. So it's conserved within the system, but it kind of goes out to the surroundings. 1/2 of 16 squared didn't need a mass again, so we've never used the mass of the block. 0.11 times 10 times x, and that gives us 116 meters. So if that's what you got, fantastic job. Hey, I want to show you just a couple more things. When you have kinetic energy, remember that it doesn't have to be translational. So by that, we mean it doesn't have to just go from one place to the other. If you have something rolling, maybe you have a wheel and it's up in the air and you're holding on to it with with an axle, and it's just spinning, okay? It has rotational kinetic energy. Most of the time when we see rolling objects like a bowling ball or a tire going down a hill or just down the road, we know that it has both rotational and it has kinetic energy. So we want to be really careful that we recognize that rolling objects have two types of kinetic energy, and that both of those make up the potential energy at the beginning. So if it starts at the top of a hill. This is kind of a great little way to do this. I have 4 objects. They all have the same mass, and they start at the top of the same ramp. They start with 120 joules of energy. When they go down to the bottom, what I want you to see is that when we look at the moment of inertia, so remember, that is based on whether the wheel, if we have a wheel, whether the wheel has a rim on it and it's just a rim, so it's a hoop, or if it's a solid disc. Sometimes we'll look at objects that roll and there'll be a ball, and a ball has a different moment of inertia than does a wheel or a hoop, a solid disc or a hoop. If you know what this decimal is or percentage, notice that if my I is 0.2 mr squared, the rotational kinetic energy is 0.2 times the translational kinetic energy. If you have 1/2 mr squared, which is pretty common to see, then your kinetic energy is 0.5 times. If it's 1, like a disk, or I guess really, like a disk, then the rotational kinetic energy is the same as translational. So the total there is 120. So all these are totals 120, but you'll see that the rotational and the kinetic can be the same. You can have more translational than rotational, so that's what happens in these two. And then you can have more rotational than you do translational. So that's kind of a more advanced topic, but something that I think some of you will truly appreciate. It makes things a little bit easier to do. The last thing that's on this slide talks about the center of mass. Notice that the higher your center of mass, okay, the more speed and the more kinetic energy it has when it hits the ground. The lower the center of mass, like in the third one, the less height and the less speed you have. This is why little kids, when they run and fall, doesn't hurt them as much as if you have a 6.5 foot person and they fall. Their center of mass is much higher, so they're hitting the ground at a much higher speed. So you just have to kind of think of it that way. So be careful with those. We're going to do, let's see, it's about 8 till. We still have about 3 minutes. I would love for you to show me here, sketch and label the graphs for the following 2 quantities as a function of the position of the block. So let me explain what you have here. This block originally was right here, and I've pushed it back against the spring. And then when I let go, it's going to go from -d to 0 with the spring. So the spring is going to push it to here, and then it's going to let go. And when it lets go, that block will move all the way over to this part. And when it gets here, it stops. And it stops because there's friction. So there's no friction where the spring acts, but as soon as the block is let go at 0, then it experiences friction. So then, of course, it slows down. I want you to try to draw the 2 curves. I want you to draw a kinetic energy curve and a potential energy curve for the block and spring system. So the kinetic energy of the block and then the potential energy of the block spring system. So I want to see what you get for this. I'm interested to see how many of you kind of know what to do. And if you don't, that's totally cool. Try to draw a curve somewhere. I see one person right now is putting dots in for their maximum and minimum, and then they're going to go back and add those curves. That is an excellent, excellent, excellent way to do it. And we've got about 30 seconds here, and I'm going to show you the answer, and then we're going to take a 5-minute break. If there are slides that I don't go through that are left, and you're going to notice that there's going to be a few left on this one, the answer is always right after the question. So you have full access to this, and all the slides are linked. So you'll be able to go in and take a look at all of the stuff that we have for you. So if you can't make it the whole time, I would encourage you to, because I think the explanation makes this make a lot more sense. All right, cool. So what we're going to do is I'm going to go ahead and show you the answer to this one. And you'll notice that this curves, oops, I'm going to go back up one. There we go. This curve's kinetic energy increases, but it's not a straight line. Potential energy decreases, but it's not a straight line. They're both actually curves. But then after that, the kinetic energy has a linear relationship with distance, and your potential energy has a linear relationship with distance. Remember, this is because kinetic energy is 1/2 mv squared. So when your speed goes up, it's actually a curve because of that square. Same thing on the way down. Potential energy of a spring is 1/2 kx squared. So you'll see that. All right, so the next question I've got the answers to, so you'll see that. But it is now break time. You have 5 minutes. Here we go. All right, 2 minutes. 2 minutes left in the break. All right, our time is up and we are done with our break. Here we go. We're going to the next section. So there are 3 sections I think that are really super important for the AP Physics exam, the AP Physics 1 exam. The first one was it was energy. The second one is momentum. The third one is simple harmonic motion. And I think they're going to have a lot more simple harmonic motion this year because they cut out, remember, electrostatics, electricity, and waves. So that really leaves a little bit more room for simple harmonic motion as well as rotational motion. But we're doing some rotational within these. One thing I just want to remind you is notice that we are using Pear Deck. So if you're not on Pear Deck, every 10 minutes or so, we will put both in the discussion thread, and then I'll try to remember to bring it up here, the code. And that code is RZQQZS. If you go to joinpd.com and then type in that code, you'll be able to get in. And then that way you can participate, which is kind of cool. So when we have you participate, you're going to be able to see, kind of whether you're on task or not, but this helps you be a little bit more engaged. So I'm hoping that really, really helps. All right, cool. So good job, way to get on. I'm seeing a lot more of you hop onto this, and that's what I absolutely love, seeing you being active and ready to go. All right, here we go. Part 2 is on momentum. So notice we're going to do this one until 6:55. Then we'll go on to SHM, FRQ tips and tricks. And then from 9 to 10, so not 9 to 9 because that'd be 12 hours. That would be multiple choice tips and tricks. This one is on momentum. And just a few things that we need to talk about. One of them is think about momentum in 2 different ways. One of them is translational. So that is going from one place straight line to the next place. And we use the equations you see there anytime we talk about linear or translational momentum. If it's angular momentum, we use the letter L to do angular momentum. I know it's weird because linear starts with L, but just remember this is angular. So angular momentum is equal to the moment of inertia times, and remember this guy right here is angular velocity or angular speed. The change in angular momentum is equal to torque times the change in time. And be really careful because on your equation sheet, you have an equation that looks like momentum. It is not. This is the Greek letter rho, and it stands for density. This is mass, and this is not velocity. It is volume. So be really careful with this equation. It is down in the bottom left-hand corner of the equation sheet. If you need an equation sheet and you don't have one, the best thing to do is type in AP Physics 1 equation sheet into Google, hit enter, and the very first link that you have takes you right to the actual College Board equation sheet. So if we move down, you're going to notice that that density equation is in the bottom left corner, okay? It's really easy to be able to find. Momentum, on the other hand, is up here a little bit higher, and you'll see it's the one with the vector sign. So momentum is a vector. It does have a direction. Density does not. So that's the other way you can kind of think about it. All right, let's go back. Here we go. Let's go to the next slide. Important quantities that you need to know for momentum. Momentum is measured in kilograms times a meter per second. We know the basic equation. We know the symbol is P. Impulse is kind of like work. If you think about work, work is the change in energy. Impulse is the change in momentum. And just like energy and work have the same unit of a joule, momentum and impulse both have the same unit of a kilogram times a meter per second. There's not a name for this. So you're not going to have like a joule or a Newton for this. It's not a derived unit. It is a unit in the basic units. So kilograms, meters, and seconds. I always tell everybody this is the most basic of all the units because it is all the basic units, kilograms, meters, and seconds. So hopefully that's super helpful for you. And maybe that made a connection that you need for tomorrow or the 24th of May. Conservation of momentum. This equation is not on the equation sheet, but remember, whatever momentum you start with, you should end up with the same amount of momentum if you're in a system and there's no loss and there's no outside force. So as long as you have that, then you conserve momentum. And you're going to use this anytime you have a collision between a couple of objects. I want you to notice, remember we talked about one graph when we looked at force and time, okay? And so when we look at this, force and distance, so when we did energy, we have force versus distance. In momentum, we're going to have force versus time. There's a big difference between the two. Remember, impulse is the change of momentum. It's F times T. So that's always going to be the area. The area of any graph is the y-axis times the x-axis. So this one, 120%. Make sure that you understand this is the area. Momentum versus time, if I do that, the slope of that gives us net force. So you might see a graph if you're taking the test tomorrow of momentum and time. Just know that this has got to be force. Why is that? Because this is the way that Isaac Newton originally wrote his second law of Newton's second law. And it is F equals ma. But it's also the change of momentum over the change in time. This is how he originally wrote it. So that's kind of a neat little thing too. Let's go ahead and do a question. Now on these, you get to grab a little dot and you're going to move that dot on one of the four answer choices. So you either want to move it to A, to B, to C, or to D. So we'll give you about 30 seconds to do this. On the multiple choice, you have about 1.8 minutes. You have about 1.8 minutes in order to get the right answer. So I'm going to give you about 90 seconds or so to answer this one. There's something that you probably need to do before you go looking for that answer. But I think you can do it without a slope. You should be able to do this without finding the slope. I'm looking at all the dots that are on the screen, and that is awesome to see all the dots and where everybody's dots are. That's cool. Good job. You guys are doing fantastic. Excellent, excellent. So I'm seeing a lot of different responses. Notice that it says the increase in momentum of the object between 0 and 4 seconds. So between 0 and 4 seconds, we're trying to find the increase in momentum. All right, excellent job. I'm seeing all kinds of different answers for this one. So let's just go ahead and let's take a look at what the correct answer is for this one. And it is 60 newtons times a second. It is 60 newtons times a second. So from 0 to 4 seconds, notice that we have, if we did a slope for our line here, you can kind of look at it, and then we want the change there, so we would end up with 60 newtons times a second. Notice that if you use slope, you're in trouble. We want force times time, so we want to find the area underneath. So we've got a triangle on top, and then underneath we have a rectangle. Okay, so that's how you want to go through and do this one. Cool. Awesome job. So let's go ahead and go to the next slide. So we'll give it a second to catch up. Cool. So here's our next question. Our next question says, a force of constant magnitude F in a fixed direction acts on an object of mass M that is initially at rest. If the force acts for a time interval delta t over a displacement of delta x, what is the magnitude of the resultant change of the linear momentum of the object? So they just want to know, what is the change in momentum? So which equation here gives us change in momentum? Which equation gives us change in momentum? These are actual AP Physics 1 questions that the College Board says are publicly available. So these are actual questions. Actual questions. All right, you guys are doing fantastic. Beautiful job. I'm starting to see a pattern here. All right, excellent. It looks like most people have answered the very first answer, and that would be correct. It is definitely force times change in time. So that would be the area. Beautiful job, guys. Beautiful, beautiful, beautiful job. Let's move on to, let's go ahead and move on to the next one. So here we go. So here's some important concepts that you need to know. We know the impulse, remember we've already talked about, that is the net force times the change in time. So your units here are going to be a kilogram times a meter per second. Momentum, same thing, is a mass times change in velocity. So again, it's just kilograms times a meter per second. And the impulse momentum theorem allows you to set those two equations equal to each other. Now, why can you do that? Because your units are the same. So that's an awesome, awesome, awesome thing. Okay, cool. So why are airbags so effective? If you look at the left side of the equation, if I can increase the time of a collision versus if I decrease the time of a collision, you'll notice that my F goes from really small to really big. So if I am in a car accident and I have my seatbelt on, then my seatbelt increases the time, okay, of the collision. And if I don't have my seatbelt on, then when I collide, it's not good. I have a very small change in time. That means the force is huge, and that's why you get hurt so badly. If you wear a helmet, that increases the impact time, decreases the force. If you don't wear a helmet and you get in an accident, then you have a very small impact time and a very large force. So let's use that. How in the world does an air mattress, and we're not talking about the little blow up air mattresses, we're talking about those great big huge ones that the stunt people use when they land, they jump off of a building and then they land on that great big blown up thing. And remember, it lets air come out really slowly, okay? So that's kind of what you want to do. What is the answer here? Does it reduce the momentum change? Does it increase the momentum change? Does it shorten the stopping time, or does it lengthen the stopping time? And it looks like most of you have it. So right now I can see I got the most dots kind of hovering right there on the answer, and that answer would be letter D. So we'll wait for this to update here. And it does. It lengthens the stopping time. So if you lengthen the stopping time, that reduces the force. And that's why it's always a great idea whenever you're out doing anything on a bicycle or on a scooter or anything else, on your Segway going down the road, wear your helmet. All right, a big concept. We always want to use momentum to solve collision problems. So if you have a couple things collide, always use conservation of momentum. If you try to use conservation of energy, it will not work for a lot of these. Don't assume that you know that a collision is elastic or inelastic. And we'll talk about the difference between those here in just a second. Don't assume that the objects stick together. So if you have two things and they are going towards each other and then they collide, don't assume that they are going to stick together unless they say they stick together. When setting up a conservation of momentum equation, remember that velocity is negative if the object is going left or moving down. Do that, because if you do that, things are going to be so much better. Okay, here we go. Let's take a look at this. These are, here we've got stick, bounce, or explosion. So this is the first thing you want to do. Look and see, what are the two things doing? They're either exploding, which means that they're one thing and they then become two things or more. They bounce, which means they're apart and then they come together and go apart again. Or they stick, where they're apart and then they come together. And they can be moving before they stick and moving after they stick, okay? So they don't always have to stop when they stick together. Then we can say, well, an explosion is the collision type explosion. We know that a stick is called perfectly inelastic, but we have a problem because when things bounce, we don't know whether it's elastic or inelastic just by watching it. What we have to do is think about the kinetic energy relationship. So if my kinetic energy is the same both before and after the collision, then we call that elastic. If I lose some kinetic energy, so for example, if I have two cars and they hit each other but they bounce apart, they don't move as far back as what they were when they came in. And that's because you lose some kinetic energy. How do you know you lost kinetic energy? Well, it goes into friction, and that friction will create sound and heat. So that's how you know the difference between elastic and inelastic. It's because they both are a bounce, but one of them conserves kinetic energy and the other one does not. That's super important. Let's go ahead and take a look at the next slide. So let's just review. Elastic collisions, no energy is lost. Inelastic collisions, we have some kinetic energy that is lost during the collisions, and the objects do not have to stick together, okay? In a perfectly inelastic collision, the two objects stick together. You still do lose energy, and you lose that probably to heat, and you know a car will crumple when it gets there. Okay, cool. Again, here's those collisions. Just one more time. I think the more you see this in different ways, the better off you're going to be. So before the collision, during the collision, and after the collision. So if it's elastic, notice that they 100% will bounce, okay? They will bounce off of each other, but it could also be inelastic. The only one that is perfectly inelastic is when two things couple together or they stick together, is what we like to say. Your turn. Here we go. We're going to do the dot thing again. I want you to drag the dot to the answer choice. And this one says a railroad car of mass m is moving with the speed of, and this says u, it really should be v. So it should be speed v when it collides with and connects to a second railroad car of mass 3m. Again, this is another AP Physics 1 question off an old exam. This is a released question, so this is one that the College Board says absolutely we can use outside of the classroom. And we want to know, is this answer A, B, C, or D? So if you don't mind, put your dot inside the box that says A, B, C, or D. Seeing a lot of good answers here. You guys are doing fantastic. So we're trying to compare the speed and the kinetic energy. So we're thinking about this collision. Doing an awesome job. I love it. Good, good, good. So I'm going to show you kind of what I'm looking at maybe here. We'll see if I can get it to lock. Okay, so we'll give it a second, and then I'm going to try to show you what I'm seeing. Let's see if it does this or not. Still moving around a little bit. There's a lot of you on, a lot of you trying to figure it out. All right, cool. So what I'm seeing is, and I'm going to unlock this, unlock screens. Your correct answer is, or at least it should be, letter A. So letter A is the best answer choice. And it is because they will have less speed. And if they have less speed, they have to have less kinetic energy because that speed's going to be drastically smaller, even though your mass went up. All right, excellent job. Let's go ahead and go to the next question. So this is another AP question that was released, so we can totally do this one. You're going to want to pick A, B, C, or D. So I have two blocks. One is mass M1, the other one is mass M2. They are moving along the same line on a horizontal frictionless surface, and they collide. When you do this one, double check that graph. Notice that that graph has both positive and negative values for velocity. So notice that one of these has a positive velocity, and the other one has a negative velocity, and then you'll see that they do absolutely collide. And because they have the same speed, this one, you know that they did stick together. So you know that they did stick together. The question is, why? So they want to know, how does the kinetic energy of the two-block system after the collision compare to its kinetic energy before? And remember, in this one, we lose kinetic energy. So this one, definitely we know that we can ignore letter D. So letter D is in dog. We do not want to pick that one. Why do we not want to pick that one? Because it says that the kinetic energy is the same, and it is not. It is definitely less. Now you have to figure out why. So we'll give you just a little bit of time here. You're doing awesome so far. Seeing a lot of good answers. All right, fantastic. Yes, this one is definitely letter A. This one is definitely letter A. It is less because the blocks had the same velocity after the collision. So because they have the same velocity here, okay, we know that they have stuck together. So some of that energy was transferred into internal energy. So, you'll hear a sound like a clang, and that's a little bit of energy that's been lost. All right. Another important concept here is during a collision or other interaction, that momentum is often conserved. Okay. So here's what you have to know in order for momentum to be conserved. Either all of the external forces acting on the system balance, or the before instant and the after instant are very close in time. So we don't have to worry about external forces, okay? And they can't really change the momentum. So we can't have anything from the outside really happening. The most common way that we write these conservation of momentum equations, and so when you get a free response, you really want to start with either this or something else that shows conservation of momentum. If two things stick together, we definitely want to use the second equation. So this one is m1v1 plus m2v2 is equal to, and then we've got m1 plus m2 times the final velocity. So notice the final velocity is the same for both, so we can factor it out. If you have two objects and they stick together, that are stuck together and they explode, so explosions don't have to be like a firework or a firecracker or a bomb. You could just have two people push each other away. And if they do that, they go in different directions. They could go in the same direction, though, but they are separate then. So those are the three biggies. Those are not on the AP Physics 1 equation sheet. The one equation that is there is just momentum is equal to m times v. So that's something you need to use. The next slide, on this one, the first thing that we have here is we're looking at, in a railroad yard, we have an empty boxcar. So we have a car, a rail car or a train car, and it's moving at 3 meters per second. So it has some momentum. It strikes a loaded car, and that loaded car is not moving. So its original speed is 0. And both the cars stick together. So we know that this one is a perfectly or totally inelastic collision. It says that each of the boxcars has a mass of 9,000 kilograms of empty, and a loaded car has an additional 5,500 kilograms of lumber. The reason that you're looking at this diagram is this is a good way of going through and thinking about what happens before and after a collision. So before the collision, it has the empty car is 9,000 kilograms, and it's moving at 3 meters per second. The loaded car is 9,000 plus 55,000, so that's 64,000. So that's one of the ways that they make these a little bit more difficult, is they sometimes make you do a few extra steps. Nonetheless, that one's not moving at any speed. So because of that, it doesn't have any momentum. So you don't see any momentum, positive or negative here. But we know that the 9,000, we have to multiply that times 3. So that gives us a total momentum of 27,000 kilogram meter per second. When they are together, that means that I've added the 9,000 and the 64,000. Then we get 73,000 kilograms, but we don't know how fast it's going. The one thing that we do know is the total momentum is still 27,000. So what I'd like for you to do is, in Pear Deck, go ahead. Here is the equation. Now, this equation is because we have a stick collision. It's perfectly inelastic. So we have to start with the momentum of the 9,000 kilogram car plus 0, because remember that loaded car isn't moving. And then that's equal to the sum of the masses times the final speed. So we're looking for that final speed. So I'm seeing some really good answers so far. You guys are doing fantastic. Super awesome. Very, very, very good. I love it. Seeing some great answers here. Excellent. Beautiful job. Beautiful, beautiful. Good, good, good. I'm seeing the right things. Seeing some great answers here. All right, looks like most of you who are doing it have it, and it looks really good. So this one, we'll give it a second to kind of come up here. Got lots going on. Yep. Our correct answer is 0.37 meters per second. So you're going to notice that we've got 9,000 kilograms times 3 meters per second divided by that total mass. So when we rearranged our equation for final velocity, this is what we got. And you end up with 0.37 meters per second. I saw that on a lot of people's answers. Excellent. Let's do one more, and then we're going to play a little game because I think it's game time. We got to keep everybody going, keep everybody happy. So we're going to play a little game after this question. We have an astronaut of mass 80 kilograms, carries an empty oxygen tank, and the mass of that oxygen tank is 10 kilograms. So 80 kilogram astronaut, oxygen tank, 10 kilograms. That astronaut is sitting still at first. And so when the astronaut pushes that, she pushes it with a speed of 2 meters per second, and then she moves in the opposite direction. So this one is 100% an explosion. Remember, explosions don't have to be boom, bam, that type of thing with all the fire and the fireworks and all that. They can just be two things pushing across each other. And when they push against each other, one goes one direction, one might go the other direction. I'd love for you to find the speed with which the astronaut moves off into space. Notice that there is 0 momentum on the left. So on the right, our momentum has to add up to 0. So we see that if we have 10 kilograms at -2 meters per second, that's -20 kilogram meter per second. So this person has to have the same amount of momentum, or +20. So now find the speed. Remember, this side of the equation is 0 because there's no velocity at all. And that's kind of the weird thing about these. You folks are doing fantastic, by the way. Love what you're doing. Beautiful job. Seeing some excellent work here. Make sure you show all your work on the AP exam. I did give you the equation, so you do not need to repeat that. But you guys are doing fantastic. I love it. A lot of really good answers. A lot of very correct answers here. Some of you are answering using fractions, and that's fine. You can do that. Sometimes that makes us go through and get out our calculators so we can figure out what you did. But that is perfectly fine. Beautiful job. One thing I will tell you is some of you are putting question marks by your answers. On the actual AP exam, just be super confident. Don't worry about putting a question mark. You know what? You'll probably get part of the credit. even if your final answer isn't correct. So always show all your work. Looking good, though. You guys are doing a fantastic job. Love it. Beautiful job. 277 of you are now on doing this, and it is beautiful to see. There's about 150,000 students that take the AP Physics 1 exam. It's pretty big, but not as big as AP Calc. Those are huge. Excellent job. All right, let's go ahead and go through this answer, and then we're going to play a little game. So we'll play a little game here. I'm going to get this moving. So we'll give it a second. Oops, nope, it's not break time yet. Whoa, there we go again. Here we go. This is definitely 0.25 meters per second. It keeps moving back and forth on me. There we go. So this was definitely 0.25 meters per second. If you don't use -2, it's going to keep doing this. Come on now. If you don't use -2 here, you will not get the right answer. So be really careful that this is, oh my goodness, that this is negative. All right, beautiful. Okay, we're going to play a little game. This game is called Gimkit. And Gimkit is a game that was created because sometimes doing these things just aren't a tremendous amount of fun, trying to go back and review things. So you're going to play this game for about 10 minutes. And you'll probably want to open a new tab. So you want to open up a new tab. And in that new tab, what we're going to do is I'd like for you to go to gimkit.com/live, and I want you to enter this code. Now, one thing that I'm going to do for those people that are watching this after we've done it, I'm actually going to go on and I'm going to play also so that you can see, you can kind of see what everybody that's playing is seeing. So hopefully that will be super helpful. If you don't mind, just put in your first name. If you don't want to do that, you could type in Mickey Mouse or something like that. But go ahead and type in your name. And then what we'll do is we will get this started here in a second. I'm going to send a link over to Brianna. And Brianna, I am putting that link in Slack. If you don't mind posting that where you are, that would be fantastic. And I am seeing a ton of people, which is fantastic. All right, so you're going to like this. At least we hope you will like this. And I'm also going to put it in Discord. So if you're in physics and Discord, you'll be able to see it there. So a lot of different places. So I think we've got everything kind of covered. It'll be interesting to see how we do with 263, 64, 65, 67, 69, 71, 72. Okay, it just keeps going up. So we'll give you just a little bit more time. Then we're going to do 10 minutes of this. Excellent job. The exam doesn't have to be tomorrow. All right, here we go. All right, you guys are doing awesome. We're up to $10,000. Good job. And we still have about 7 minutes left. And if you're watching the video, you can see me going through and answering the questions here. So hopefully you're taking a look. I'm trying to take my time so that you can answer them first. Little less than 4.5 minutes left. You guys are doing fantastic. We've got Watermelon in second, Sarah in first. Sam, well, there's Donna, then Sam, then Aditya. Good job. Don't forget, you can use the power-ups here. Make more money per question if you want to. Oops. Oops. Didn't read it. Oh, it just got blurred. All right, we're up to $193,000, $198,000. Got about 2 minutes left. 2 minutes. Woo! We've been iced. Donna is winning. Sarah, Watermelon, Caroline, and Sam up at the top. You guys are doing good. Good job. Oh, thank you for the gift. I got a gift. Some of these are super easy. Some of them take a little more thought. All right, excellent job. Here we go. These are our winners. Elle came in third, Watermelon in second, and Sam came in first. And then we've got all the other people. Nice job, folks. You did fantastic on that. That is beautiful. Yes, please give yourselves applause for doing such a great job on the Gimkit. All right, just a couple more things that we need to do in terms of momentum. Okay, so a couple more things that we can look at in terms of momentum. Remember, on your AP Physics 1 equation sheet, okay, there are two equations for momentum. Our first one is momentum is equal to mass times velocity. And then our other one is the change in momentum is equal to force times the change in time. Do remember there's some equations that deal with momentum that are not on the equation sheet. For example, the conservation of momentum is not there. So you got to be really careful that you know how that works. But other than that, that is really it in terms of what we're looking at for momentum. So we did all of the equation things. And so I'm going to move down here. I want to go back for just a second, and let's take a look at just a couple of things here really quick. And so there's a problem that we did not do that I would love to look at for energy. And so this one is really kind of an important one. So we're going to go back to it. Since we've got about 5 extra minutes, that gives us time to go back. So we might do that a couple of times. And here it says that we've got a projectile launcher. So we have an uncompressed spring. And we're going to take a sphere and we're going to press it against the spring. And then it's going to lock in with this little pin here. Okay. So it is definitely some sort of, some sort of little cannon. So it says a student hypothesizes that the spring constant of the spring inside the launcher has the same value for different compression distances. So what is a basic physics principle or law that the student could use in designing an experiment to test the hypothesis? And already I've got a bunch of people that have put a bunch of stuff in, and that is fantastic. You guys are doing beautiful. There are a couple different answers for this. And so no matter what you put, it's probably one of the two. But this is fantastic. You guys are doing beautiful. I love to see all these answers pop up. Awesome job. Very good. And so you're going to see here a couple of different answers. One of them is Hooke's law. And remember, Hooke's law is just the force of the spring is equal to the spring constant times that compression or extension of the spring. So either one of those is absolutely fine. The other one we can use is conservation of momentum, conservation really of energy. I think they meant energy here instead of momentum. But they did write momentum. We really want energy there. And so that is US is equal to KE. So good. So this person actually put both. And so we love that also. Good, good, good. Excellent job. So either of those could be an excellent answer for this. And so you'll see that. Now that we've done that and we know that we can use conservation of energy, that's kind of what I like to use for this one, because it's really not as, well, you could use Hooke's law and still do this pretty easily. So either using conservation of energy or using Hooke's law, what I'd like for you to do is give me an expression in terms of quantities that can be obtained from measurements made with equipment usually found in a school lab, and I want you to solve for K. Let's do this using energy. So if you said Hooke's law earlier, let's go ahead and use energy here. So if you don't mind, let's use energy. We're going to go from spring energy over to kinetic energy, and then go ahead and solve for K. So this should be somewhat easy to do. It shouldn't be awfully too bad. Most of you are already done, it looks like, which I love. That's awesome. Beautiful. But let's use energy. You're going to see that if you use the Hooke's law, that's super easy. But the problem is you're going to have to use the force of a spring. All right, seeing some awesome answers here. So we'll take a look at the answer in just a second. We want to give everybody a little bit of time here to just maybe go in. And try to type an answer or write an answer. You guys are doing fantastic. We're almost at the end of hour 2. You guys are rocking it. Beautiful job. Okay, so let's take a look at the answer. This one's pretty easy to do, so it really shouldn't be too bad. You're going to notice that we start with spring energy. We go to kinetic energy. So we have 1/2 kx squared, which is spring energy. And we go to 1/2 mv squared, which is our kinetic energy. And that takes us to K is equal to mv squared all over x squared. Remember, x squared is the compression. It's not the distance that it travels when it gets shot out of the launcher. It is how far we compress the spring. So notice that you could use this and you could actually then find that value. So excellent job. Very, very nice. All right, it is break time again. Let's break it out, and then we will come back and spend a little time with simple harmonic motion. Here we go. All righty, break time is over. We are going to move on. Here we go. Next topic that we're going to do is simple harmonic motion. So kind of like what we did last time, I'm going to put the link again up. So if you are not on Pear Deck, we would love for you to be on Pear Deck, because that way you are active. You're able to type things. You're able to answer multiple choice questions. Just a little bit better way to do it. Keeps you engaged in what we're doing, and hopefully helps you on the test tomorrow. So that's our big key, is to get you going. So if you go to joinpd.com, the code here is RZQQZS. I know it's a little hard to see up in the corner, but I know Brianna is doing a fantastic job answering some questions. Okay. She's also doing a great job of making sure that you have that code if you need it. So, all right, awesome. Here we go. This is simple harmonic motion. We're going to do this till 7:55 Eastern time. So if you're in Central time, it's still 6:55. Then after this session, we are going to do the free response tips and tricks. That one, super important in order to get some points. Remember, every point you can get you closer to the 5. And then we're going to do multiple choice tips and tricks. We will play Gimkit again. Do the same thing I'll play for those people that are watching the video or can't play along. So I think that is about it. All right, here we go. Simple harmonic motion. Remember, one of the places I like to go for review is flippingphysics.com. But if you go to college and you do that, you'll notice that you'll be able to use a lot of these things. Again, a lot of the resources that you've seen that either we've introduced you to or somebody else has. Okay, on the equation sheet, there are not as many equations for this. However, when you do simple harmonic motion, you will also be doing a lot of energy. And so we're going to go through that just to make sure everybody is super, super set on this. Your first equation here is x is equal to a times the cosine of 2 pi ft. I have a lot of students say, I've never seen that equation. That one's not on the equation sheet. Yeah, we better pull it up so that I can show you where it is. All right, here we go. You'll notice that up at the top we have kinematics. Then we have dynamics or forces. That includes some acceleration, some circular. Here we've got momentum. Then we've got energy, work. Here's power, rotational. And then suddenly in the middle of the rotational stuff is this guy. And this is that equation that we were just talking about in the Pear Deck. And it is the one that tells you where something is. It tells you exactly where it is. And it's equal to the amplitude times the cosine of 2 times pi times the frequency with which something is turning times the time that we're at when we want to know where something is. So when I look at this picture, you'll notice that this is position. So the little dot here is what you can solve for with that equation. We can tell where on this curve that little dot is at any particular time. So one more time, the dot that you see that's moving here, if I stop it, and I can't stop this, it's just an animated GIF, but if I stop it, I can figure out exactly where it is on this position line by using the equation x is equal to a cosine of 2 pi ft. And so that's the same equation that we're looking at here. Not a very used equation, but still something that is on there. Okay. You'll also notice that in Discord, Peter Apps, our awesome physics teacher who is also in charge of all things science at Fiveable, has posted a link to Dan Fullerton's AP Physics 1 Simple Harmonic Motion video. Really great. He does a lot of math. And so if you like the math into this, he is the man to watch. Okay. The other 3 equations here are just the equation for period. It is 2 pi over omega. Remember, Omega is angular velocity, and that's also equal to 1 over the frequency. Here we have the period of a spring and the period of a pendulum. Remember, pendulums depend on the length of the pendulum and gravity, not on mass. There's no mass here. This one, the spring length doesn't matter, but the spring constant and the mass attached to the spring sure does. So be really careful with those. Important quantities that you really need to know: amplitude. Remember, that is the distance from where the spring is relaxed to either where it's compressed or it's extended. So we'll look at we'll actually look at an equation, or I guess we'll look at a graph that will show you what that really looks like. There is no equation for it. The spring constant, remember, that one is super simple. That is found in force, that is found in energy, and that's also found in simple harmonic motion. That is a super important. Remember, that's how strong a spring is. And the basic equation for it is the force of a spring is equal to the spring constant times that compression or extension. So here are our equations. The top two are on the equation sheet. The bottom two are not. So we'll quickly go through the top two. This is a spring that's oscillating. It can be up and down, left and right. The more firm the spring is, so if it's got a high K value, it will have a really short period. It will bounce back and forth very, very quickly. A slinky would have a very large, would have a very small K value, and so that one takes forever to go up and down. A pendulum, this one is anytime you have a mass at the end of a string, it's the mass doesn't matter. It doesn't matter how heavy it is, okay? So it's just the length of the string, and then if you're on Earth, G stays the same. If you go to another planet, then G would change and your period would change. The angular frequency of a spring mass oscillator, this is the angular speed, okay? So that's the speed as it rotational, so think about rotational motion. Just remember this. You don't need to memorize the equation. Instead, remember the above equation. So remember this equation. It's just 2 pi over t. You don't have r here. If you put r in it, this becomes v. So remember, the link between the rotational things and the linear things is r. So if I take the r out, this becomes rotational velocity. It's also equal to the square root of k over m. The last one is the total energy of a spring and a block when they are oscillating together. That is equal to 1/2 mv squared plus 1/2 kx squared, and that's equal to 1/2 ka squared, okay? So the total energy is constant throughout this, but it trades off between the kinetic and potential. So it's either mainly kinetic, mainly potential, half of each one, but in the end, it always adds up to the same amount of energy. These three graphs are super important. And they're super important because they are the position time, velocity time, and acceleration time graphs for things that are moving with simple harmonic motion. You have seen this for when things travel in a straight line. We know position versus time might be a curve or a straight line. Velocity time is typically a straight line. Acceleration time is usually just a horizontal line. That's when things move in a straight line. But when they are oscillating, we get these, either this is a positive sine curve, this one is a positive cosine curve, and this one is a negative sine curve. So you'll notice that each one of these, depending on where the first one starts, the second and the third will change. Here, the displacement varies in a sine, okay? The highest peak and the lowest trough is basically just the amplitude. So amplitude would be from the middle line up to the peak, or from the middle line down to the trough. It is not from the top down to the bottom. It is just above the line or below the line. So that's what A is. If this is velocity, then we just take take that distance, so the amplitude again, and we multiply it times the angular frequency. That gives us the linear velocity. And then finally, the acceleration here is just the amplitude. So that's how high the peak is or how low the trough is. and we multiply that times the angular frequency squared. So those are the three equations. Now, let's look at how these work. Notice that this is position versus time, and it's position in radians. As this one, you'll notice, is moving, you'll see the velocity, okay, as it changes. So this is velocity in meters per second. So when this one crosses the line as position versus time, so when it gets to 0, notice that we have a lot of speed, a lot of velocity. Same thing at the top here. So when this crosses the 0 line for position, we have a lot of speed again. So it's kind of like a pendulum if you think of it that way. The last one is acceleration. And you'll notice that this one is a camel hump down. This one is a camel hump up. So these two are exactly inverted. So these two graphs are inverted. All righty, let's go on to the next thing. If we think about these graphs, but instead of position, velocity, and acceleration, we're going to look at energy. So potential energy versus time, kinetic energy versus time. Notice that neither one of these ever are negative. Why is that? It's because when we do the potential energy of a spring, it's 1/2 kx squared. So here A is just x. And then kinetic energy is 1/2, and then it's the same thing, 1/2 mv squared. So it's some constant, so that's our mass, times the amplitude squared. For potential energy versus displacement, it makes this curve, and kinetic energy versus displacement makes this curve. So just pay attention to the axes. Make sure you see that time gives you these sine graphs, and position will give you either this graph or it will give you this graph. So either concave up or concave down, depending on what you're doing. All right, time to practice. We have a block hanging from a spring. It's at position B. The period of the resulting, and we release it at time 0. And what it does is it makes this velocity versus time graph. What I would like for you to do is use your drawing tool, and I want you to draw the curve of momentum versus time. So here, t is the time for one cycle. So you'll notice that this is one complete cycle. So if this thing is going left and right, it goes to the right, it goes to the left, and then stops at the center. It doesn't really stop. It's going to keep moving, but that's what we're measuring. So what I'd like for you to do is I want you to draw the curve. What would the curve look like for momentum? The big hint here is velocity is up atop. Momentum is down below. Think about the equation for momentum. What is your equation for momentum? If you remember the equation for momentum, you should be able to draw this graph pretty easily. Yeah, I'm starting to see some good answers here, so you guys are doing a good job. I asked Brianna how things are going on her end over there with the chat. She says that you guys are rocking it out, and that's fantastic. I have seen some questions about the number of points it takes in order to pass the exam. I'm going to help you with that a little bit later. So you guys are doing a good job. There is an AP Physics 1 score calculator if you ever want to use it. All right, so seeing some great graphs. Here's the deal. We know that momentum is mass times velocity. So the answer for this one is you should get the same shape. You should get the same shape. And if you want to be super technical about it, and if we said that this is 1 meter per second, this is 2 meters per second, and you multiply it times mass, and that mass is bigger than 1, then you could say that this would be like 2, and this would be like 4. But you'll see that the curve is basically the same shape. Why is that? Because remember, momentum and velocity are directly related there. As one goes up, the other one goes up. So this one, we have the acceleration versus period graph. And notice that again, the period includes one cycle. So you want one cycle to go by when we have this one. So it says the block is pulled down a little bit, and then we let go, and it accelerates up, and then it accelerates kind of in the negative direction, and then boom, and keeps going back and forth. We want you to graph the force versus time graph. So here's acceleration versus time. I want you to go ahead. I want to see what is the force versus time graph. Some of you have already started. You've done an excellent job. Be really careful that you make these a curve. It's super tempting to draw straight lines. You just really want to make sure that they curve as you go through. Good job, Lucy. Eshna, good job. Paige, excellent. Ariana, good. Kritika, excellent. Fergan, good. Some beautiful pictures here. Carly, excellent. Samantha, nice. Rhea, good. Foxtrot, beautiful. Rupkatha, very good. Kinshuk, very good. Excellent, Mike. All right, cool. So this one, again, should be pretty easy to do. You should get, oh, it's stuck again. We'll have to give it a second here. Nope, we're going to back up. Went too far. We're going to go back again. Back again. Back again. Back one more time. Just got to wait for it to catch up here. It's internet based. All right, here we go. So there it is. That is our answer for force versus time. So there's our momentum again. We'll just got to give it a second to catch up here. Got so many of you on. It likes to play games with us. All right, here we go. So it does look the same. Remember, F is equal to MA. So if your A is up high, your F is up high. If your A is down low, then this one is also down low. All right, good job. So let's go ahead and take a look at the next one. This one is position versus time. The bottom one is potential energy for the block spring system. So this would be both kinetic and, I'm sorry, kinetic, losing my mind. This would be both spring energy and potential energy due to gravity. So think about that. So we want to graph a potential energy for this block spring system. And let all your vectors quantities be positive for the upward direction. So if it's going up, it's positive. All right, seeing some good answers here. And we've got the period here. So for position time, this is what you want. Starting to see some good answers here. Excellent job, Emma. Good job, Gabriella. That's good job. Dal, you're good. Excellent job, Victoria. All right, let's take a look at what the answer should be for this one. So I'm going to click it one time. So hopefully it just goes once. And this is the correct answer. So notice, because this one is down below, here it's moving at a high speed, so you don't have any potential energy. Then it gets to the top and it stops, right? And so it's stretched here. So now we have spring energy. Okay. So this one, you're actually going to get 2 cycles where you only had 1 cycle for this one. And remember, it's because our spring energy is 1/2 kx squared. So that one's a little bit more difficult. Let's go ahead and take a look at the next one. Let's look at the next one. Okay, so for this one, we have velocity versus time, and they want you to do kinetic energy versus the period or versus time. So this one's a little bit easier to do, I think. Seeing some great answers here. Again, remember, think of the equation for kinetic energy. And because it is 1/2 mv squared, if you have a negative velocity and you square it, that means it's got to stay positive. I'm doing pretty well on this. This is not easy sometimes here. But you guys are doing fantastic. All right, let us. Here is their answer. So notice when it doesn't have any speed, it doesn't have any kinetic energy. Here it's got maximum speed, maximum kinetic energy, no speed, no kinetic, maximum negative speed, but you're going to have maximum positive energy again. Then 0 speed, 0 energy, and then it just keeps going on. So this one is very similar to the one that we did earlier with potential energy. And remember, it's because of the squares that we end up having some of the other things. All right, cool. Next one. We do have a block hanging from a spring. Whoops. It's going to keep going back and forth on us here. It'll stop doing this in just a second. There we go. Block hangs from a spring. It's just confused. Don't ask me why. All right. Here we go. Just going to click one time. Maybe it'll go where we want it. All right, good. So we've got a block hanging from a spring. Might have to yell at it here. Oh, my goodness. Okay, so we'll give it a second. Come on now. I think I might have. Yeah. All right, so what I'll do is I'm going to just stop this for just a second. We're going to log back into it again here in just a second, just because it's kind of doing whatever it wants to do here. Okay, so we're going to go back into it again, and we're going to pick up right where we left off. But the let's see, the Pear Deck code is going to, it's going to change. Control-Shift-C, there we go. So now we've got a new code. So it is TEGEWI. So we're going to have to change. Sorry about that. But it started to freak out on us a little bit. I'm going to put a link in for Brianna. So we'll give it a second here to kind of chill out. And there we go. And so I'm going to send the link to Brianna, and then we'll have everybody log back in again. Sorry about that. And here we go. Now we're getting somewhere. Good job, guys. Thank you for being patient. Thank you, friends, for doing such a good job here. And Brianna, I did put that back into the chat. Thank you, Peter, for doing it. And oh, yeah. So good resource for simple harmonic motion graphs. Oh my, go to flippingphysics.com. And flippingphysics.com, you will see a whole section on those SHM graphs. So flippingphysics.com. If somebody has time and you can go there and find where those are and put them in Discord, that would be awesome. And then if Brianna, if you don't mind, if you find them, if you can do the same thing, that'd be great too. All right, cool, guys. Hey, thanks for being super. Oh, beautiful. Thank you. All right, here we go. Thank you for being patient, folks. Thank you for getting back onto the Pear Deck. And I'm going to move down to where we were at. And we will just keep rocking it here. You guys are doing a fantastic job. We are in the middle of simple harmonic motion. We have drawn almost all the graphs that I want you to draw. But here's the next one I want you to draw. So for this one, notice we do have a block hanging from a spring. The block is pulled down a little bit and released. Sketch the graph of the total energy versus period. So sketch that graph of total energy versus period. BJ Moon put in Discord the flipping physics video. It is phenomenal. Thank you so much for doing that. That is beautiful. And those are the graphs of position, velocity, and acceleration. I'm going to copy that. I will send it to Brianna, and she will put it in the Vimeo chat that she's in. So thank you for doing that. All right. And so I'm going to take a look at what everybody is doing here. Dash. All right, you guys are doing great. I'm actually going to do this on a different app here. Just make sure I can see it okay. Excellent. Good. Good, good, good. All right. So our answer for this one is a straight line all the way across. Remember, if we have total energy, as long as we're not losing any energy to the surroundings, which we're conserving energy here, then this is what we want. And we want to see that the energy is 100% total. Okay. So 100% total energy. So nice, nice job. Beautiful job. Okay, so just some important concepts. Periodic motion describes any motion that repeats over and over and over. Okay, it's like a little kid that just keeps saying the same thing over and over, or little kids like to watch the same TV show over and over. This can be uniform circular motion, simple harmonic motion, like we're doing orbits, whether circular or elliptical. If you have a puck on an air hockey table and it bounces back and forth without ever losing energy, that's periodic. If a golf ball bounces on the floor back up to the same height and it continues to do that forever, that's periodic. It's when you lose energy that it stops being periodic. Okay, so there has to be an equilibrium point, and there must be a net force acting on the system that's always pointing towards equilibrium. We know that simple harmonic motion is really simple because it's periodic motion that is the simplest to model. So that's where our equation comes in. There are three things that you have to have that are true in order to have an object be in simple harmonic motion. The net force has to be proportional to the displacement. The object's motion can be modeled as single sine or cosine graph. So that's why it's so important to know those graphs. And then the period is independent of the amplitude. So the period will not change when the amplitude changes. So here are some graphs that kind of show that. This first one is a spring that is exerting a force. So this is a spring in a mass. We see that that means that the spring exerts a force that's directly proportional to displacement. So that's good. The second one shows that the period is the same regardless of the amplitude. So I've made the amplitude bigger here. You'll notice it's bigger here, but the curve always shows the same period. So 1 period is just this 1.5 seconds. And we do it again. Then the last one, the period and the amplitude don't have a relationship. So you don't see a relationship. So we just have this non-relational line there. For the next one, this is a pendulum. Now notice that a pendulum, when we do pendulum experiments, we always do them at very small angles. So up to about 30 degrees, it behaves. It does what it's supposed to. If you have it swing too far, if you've ever been on a swing and you swing too far, you kind of bounce a little bit, that's where we've gone outside of our criteria. So we really want to keep the swing small and all 3 things happen again. So that's good. A bouncing golf ball, notice it doesn't do that. So we have an initial force in height, and you'll notice that you've got the 1 dot and then it's just kind of flat. You'll also notice that the height and the bounce time is different for when it bounces when it's not very high versus when it's up very high. And then there's definitely some sort of relationship here between period and amplitude. So bouncing golf ball does not meet those criteria. Here we go. We want you to answer this. A simple pendulum. Now, this is an actual AP question off an old AP test, and they told us that we can use this. These are released AP questions. So you'll see this. A simple pendulum consisting of a small object of mass m is attached to a spring of length L has a period T. They want you to go through and figure out which answer would be the best. You guys are doing absolutely fantastic. Love it. Good answers so far. Awesome answers. All right, so the answer to this one is definitely letter A. And it is m/2. So we have to divide our mass by 2, and our string length would stay the same. So notice that the only thing that changes here, the only thing that changes is the mass, okay? So, and when you change the mass, it doesn't change the period. Leaving the string length stays the same too, okay? So that one is just super important. Periodic. Okay, so let's go ahead and go to the next question. A simple pendulum and a mass hanging on a spring both have a period of 1 second. They're set into a small motion. They're taken to planet X, which has the same diameter Earth, but twice the mass. Which of the following is true about the periods of the 2 objects? All right, good. I'm seeing some great answers here. You guys are rocking it. Beautiful job. Excellent. All right, let us take a look and see what the correct answer is. Yeah, the period of the mass on the spring is shorter. That of the pendulum is going to be the same. So remember, the mass makes a difference. but the pendulum, mass makes no difference, okay? So be really careful. All right, nice job. Next one. A block is attached to the lower end of a vertical spring. It oscillates up and down. The spring does obey Hooke's law. And the period of oscillation depends on which of the following. Is it the mass of the block, the amplitude of the oscillation, the force constant of the spring? So it's either just the amplitude, just the force, the mass and the amplitude, or the mass and the force. So let's see which one you pick. Seeing some good answers again on this one. Nice job. All right. So this one, definitely the answer is 1 and 3. Remember, amplitude does not matter, but the mass of the block does, and the force constant of the spring. So remember, that's K. So you remember our equation, we said that for a spring, we would have TS is equal to 2 pi times the square root of M over K. So that is our equation we would need to use for this one. Good job. Okay, so it's really not break time, but I will tell you what time it is. It is definitely time to go back and let's do Pear Deck again. So let's go ahead and I'm going to pull up Pear Deck. We're going to do a little simple harmonic motion here with Pear Deck, and we will get you started. But I think this is a great way to go back and just kind of review a little bit. And so we're going to do this one for 13 minutes. We'll go back and kind of review simple harmonic motion a little bit. And then we're going to spend a plenty of time going through and doing some things with our good friend, free response questions. And I've got plenty of tips, tricks, all kinds of things. So if you have friends that signed up and aren't on yet, definitely want to have them come on now. I'm going to send this to Brianna. So Brianna, just put the link, sent the link to you. And I'm going to do the same thing in, yeah, you guys like Gimkit, I'm assuming. Gimkit's fun. Gimkit is fun. So Gimkit is now in our good friend Discord. And I'm going to play also. And so we'll make sure that people that are not able to join us can see kind of what the Gimkit questions are. And you can see that on my end. And I've got to just put the link in. You guys are doing fantastic getting into Gimkit. Really, I think this is super helpful. These questions are somewhat easy. At least we hope so. And I think everybody's getting on. You guys are doing a great job. We'll give you a little bit more time. Good job. All right. If you're not on yet, just look for the link in Discord, or Brianna has put it down at the bottom, and you'll be able to see it there. I'm going to give you 5 more seconds to try to get onto it. Everybody loves the Gimkit. All right, here we go. And for those of you watching the stream, you want to see what we're doing? This is it. Oops, sorry about that. Okay, we've got 10 minutes, 10 visits, 10 minutes. square. It's a square. Uh-oh. Yep. We should have about 3 minutes. 3 minutes. Oops. Sorry about that. Period should increase on that last one. It's 2. Should have about a minute. Time should be ending here soon for this one. Click a few here. Oops. Let's see if it behaves a little better. Time should be ending here in a second. It looks like alrighty, so that one actually locked up on us a little bit. Sorry about that, guys. So we don't know who won, but that's okay. So not a big deal. Alrighty, so I think what we'll do is we're going to, oops, go ahead. I'm going to have to exit that because that one kind of burned out just because we were doing so many things. Remember, for simple harmonic motion, I think some of you are asking about some of the curves and things. Probably the best thing to do is there is a really good flipping physics video that does a great job of going through all those curves. And somebody actually put it in the chat. So let's see. I'm going to put it in. I'm just going to bring it up really quick so you can see what it looks like. All right, so we're getting there. Let's see. Yep. All things. All right, there we go. And all right, we had one. I think it'd be easier to just go to flipping. If you go to the flipping physics site, so tomorrow or tonight when we're done, if you want to do just a little bit more, if you go to physics videos and go to Physics 1 teachers, it's okay to do that. That's not a big deal. There is simple harmonic motion. And then when you go there, you're actually going to see simple harmonic motion. You're going to see all of the videos that he has here. And here is the position, velocity, and acceleration graphs. So when you click on that, it's that same thing that I was showing you earlier, but he does a good job of going through location and notice really kind of explaining what those graphs look like and why they look like that. So if you really want a little bit more, you're going to start to see that again. It might be a little bit. Yeah, so that's a really good video. Videos are all super short. They're under 10 minutes a piece, and they're pretty easy to see. There's also lecture notes with each one so that you can see how, or, you know, kind of what students would write down for a lot of these videos. Here's our equations again that we talked about. This one's in a little bit different form. That's okay. But if you remember that equation we said that doesn't get a lot of attention but gets used every once in a while, you'll see it right there. That's in those lecture notes. So same type of thing. So a good thing to kind of take a look at. Go to flippingphysics.com, take a look at that, and you should be set. All right, we are up against a hard break again. So we will do our hard break, and then after the break, we are going to hit free response questions really hard. Then we are going to take a look at multiple choice. So we're actually going to do some free response. We're going to look at all the different types. And I think that's super important to do. So 5 minutes, and we will come back, and we will go from 8 to 8:50 with that, 8:55. And then at 9 o'clock, we will go to 10 and finish you up. And then y'all need to take a break, especially if you've been on for 5 straight hours. All right, here we go. Go take a break. All right, here we go. Hour 4. You've got to be kidding. This is blown by. You guys are doing an awesome job. Let's talk about free response questions, tips, and tricks. We're going to do this till about 8:55, and then we'll take another hard break and kind of move from there. So we're going to take our time going through this just because I think you really just want to make sure you know what's coming. Please, 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 when you do this part, take your time. You don't have to answer every single thing. It's better to answer what you know and answer it well than to try to answer everything and not do a very good job on any of it. So start with the things that you absolutely know. If there's topics that you have not gone through, for example, if you haven't done rotational motion, skip over the rotational motion question if there is one and do it last. Go back and then just use the equation sheet to kind of do the best you can. There are 5 free response questions. You do have 90 minutes. This you will take after you do the multiple choice. So you do multiple choice. Remember, it's 50 questions. That takes 90 minutes. You get a really short break, and then you're going to spend 90 minutes, and you should be busy that entire time. So when you do this, 2 of these questions are 12 points. They always have been 12 points. They always will be 12 points. They suggest that you spend 25 minutes on each one. If you spend more time, that's fine, but then you need to find time that you can spend less time on, or find questions you can spend less time on later on in the exam, or you might save some time. So go to the one that you think is probably the easiest one for you to answer. Do it first, and then just keep track of your time. One of the things I didn't really say that you probably really need to make sure you have, you cannot use, when you go into the testing room tomorrow, if you're taking it tomorrow, you cannot wear an Apple Watch. You can't wear a smartwatch at all, because you can get answers from that. However, if you have just a regular watch, you might take it with you, because you can have a regular watch. It can't beep, the alarm can't go off, so turn all that off. But a regular watch might really kind of save you, especially if the person who's proctoring your test forgets to tell you how much time is left. And that happens sometimes. So either make sure there's a clock in the room if there's not demand that they have one somewhere. But really do yourself a favor by taking and making sure that you, oh shoot, what am I going to say? What is it that I want to say here? Make sure you take care of yourself. So get some sort of clock, okay? And do it that way. I think that's the best thing. Quantitative, qualitative translation, experimental design. Then there are 1 paragraph length and then 2 short answer questions. So really read each one of the free response questions and then do the ones that you really are ready to do first. Okay, there are some key terms here that are on the exam. This is also in the great big file that is called the course and exam description. They even give you these in the student information on the AP website, but I'm going to give you the ones here that you really need. Calculate. This means you need to show all of your work. Notice, if you don't show all your work and you just put down the number or the final algebraic expression, you probably won't get any points. You have to show all your work. So if you remember, we were going through and we were doing the ones with, that are really kind of interesting. So the ones, and energy, if you remember that, those are, you had to start with conservation of energy. So like US is equal to K. Put that down and then do your equations. 1/2 kx squared is equal to 1/2 mv squared. Show all that work. Even if they ask you a what is or determine, you don't have to show your work, but showing your work leading to answers is a good idea because you still can get partial credit for a lot of those. So calculate and then what is and determine. So those are super important. This is where you really need to take your time. Justify and explain. They want you to support your answer by prose, which means you're going to write a sentence or two, equations, calculations, diagrams, or graphs. The prose or equations may refer to fundamental ideas. So they might talk about Newton's laws. Usually it's the second law. So acceleration is equal to force over mass, or the net force over mass. If you've been in some of my streams earlier, you know when we do Newton's laws, we never talk about just force. We always say net force or sum of the forces, because that is what we need. Conservation of energy, conservation of momentum. Those are all the things that you need. In other cases, the justification or explanation may take the form of analyzing behavior of an equation for large or small values of a variable in the equation. So what would happen if you increase the K value in Hooke's law? What would that do to the force if your stretch is the same? So that is what they mean by analyzing the behavior. If we look at the next one, this is called derive. And we're going to practice this a little bit. This means you have to begin your solution with one or more fundamental equations or physics principles. Typically, you're going to start with what we show here. Either Newton's law, second law, conservation of energy, or conservation of momentum. Show all the steps, use all the symbols given, Don't use your own symbols. They will tell you what they want you to use. So stick to those. You might do some things that are unique to what your teacher does or what you do in class, but when they give you symbols, make sure you do those on your own. All right. I told you we were going to practice. Here we go. Let's practice this. We have a car of mass M. It's up at the top of this hill. There's no friction. So when it says negligible, you can ignore friction. And it's going to go down and then come up, and then it's going to come up the hill and then come back down the circle and come out. Okay. Assume the center of the mass of the car is at a height equal to the diameter of the loop. So now we can just say that that car, when it's here, we can just assume that the center mass is at the same spot. In terms of given quantities and any fundamental constants, they want us to derive an equation for the speed at the top of the loop. You don't have to worry about rotational kinetic energy. Now, I know some of you are probably already working on this, and that is absolutely fine. However, we're going to go back a slide. So if you're working, I'm just going to go back one slide here for just a second. And when we go back this one slide, or actually I want to go back 2 slides. So we're going to go back one more slide. Here we go. Newton's laws, conservation of energy or conservation of momentum. So when we do this, we want to use Newton's laws, conservation of energy, or conservation of momentum. When you see, now we're going to do this back and forth thing again. When we see this, okay, I'm going to go forward. Here we go. Whoops, I don't want to show you that. When we see this one, notice we go from one height to the other. It's not colliding, so we're not going to use momentum. There's really not any force here that we worry about, so we are definitely going to use energy. I want you to use energy to do this. We're looking for the speed at the top of the hill, okay? And the given quantities here are MC and H, D, H, and MC. So D, H, and MC. Those are your variables. And then, of course, you can use V. So they want you to find the speed at the top of that loop. So it's an inside loop up at the top. And you guys are already on it. I love it. You guys are doing a great job. Beautiful job. Excellent, excellent. You guys are thinking. Job, Samantha. Job, Sarah. Beautiful job. Nobody's asking about air resistance, which is good because remember, we can ignore air resistance. And they also told us here we don't have to worry about rotational kinetic energy. So that's good too. Excellent job. Seeing a lot of great answers again. All right, let's go ahead and take a look at the answer for this one. A lot of you had it, which I'm super happy with. This is not an easy one. So here we have final kinetic energy. So we know we have some kinetic energy here, and we still have some potential energy due to gravity. We don't have as much as what we started with, but we do have some. At the top, we only have potential energy due to gravity. So now what we did is we said that K is equal to 1/2 mv squared. and I know UG is equal to mg delta y. And so we plug those in. And when we did that, we see that we have H and we have D. And when we just factor out the M and the G, we get H minus D. Then we just square root both sides and we end up with our final equation. So excellent job for those of you that did it. You don't have to separate out the 2G. You could leave it in. It could be 2G capital H minus 2G D. And notice we've used all the letters that were here. G is a constant, so that is a fundamental constant. And so you can use it within the equation. 2 is a constant, just a number, and it doesn't change. So excellent job. Nice job. Okay, sketch versus plot. Sketch and plot relate to graphs. One of them means you do not have to show any numbers, no data points. You're just going to draw the curve. That's all you have to do. Plot means you have to show your points. You have to show the scale. You have to put in a best fit line or a best fit curve, depending on what's going on. Usually with plot, that is a graph where you have to put in a best fit line. Okay, so let's talk about some of the different types of free response questions. The first one is a qualitative quantitative translation or a quantitative qualitative translation. I've seen it both ways. It doesn't matter which one goes first. Qualitative. So this one, usually when you start with the quality part. So this is where you're not using any math. We're really just talking about the physics principles that are involved. So it might be conservation of energy. It might be momentum. It might be simple harmonic motion. You might be using Newton's law. So any of those. Qualitative does not mean that you just write an equation in words. So if they say, you know, explain what's going on and you say K is equal to 1/2 mv squared, that is not qualitative. If you write kinetic energy is equal to 1/2 of the mass times the velocity squared, and you write that out in words, that still is not qualitative, okay? You really need to explain how the physics principles apply. So like in that last one, we would say the object starts with all potential energy, and then it loses potential energy to become kinetic energy at the bottom of the hill. And then when it climbs back up to the top of the loop, it still has kinetic energy and it has less potential energy than it did at the top. So that is what you really want to do. Quantitative analysis, usually in this, you're deriving expressions from physics principles. So again, net force or Newton's second law, conservation laws. So that's either conservation of energy or conservation of momentum. Translation. This is the T part, and we're looking for relationships. So how is it when I have F is equal to MA? If I increase A and M stays the same, then F has to increase. So that's directly proportional. If M goes up, A goes down, but F is supposed to stay the same, then M and A are inversely proportional. So we're always looking for that translation or those relationships. So look for a really clear correlation between that qualitative and quantitative. So when you mention all the things about the energy and then they ask you to derive an equation, you've gone from talking about it in qualitative means to showing your equations in quantitative. So good job. Graphing tips. So let's go back to graphing. Always include a scale, your variables and your units. Make sure you have a ruler. So we've talked about this a little bit, but make sure you have a ruler to draw your best fit line. If it looks like it's curving, when we go to grade it, we have to grade it as a curve, which means you won't get full points for that. If your data is not linear though, and you're supposed to draw a smooth curve, don't use a ruler to do it. Just draw the best curve that you can, okay? If there's two curves on the same graph, make sure you label each one. I think we did a question just like that tonight, and y'all did a really good job with it. Now, you were able to use different colors and things, but if you can't use different colors and you really want to show how they're different, you can make one a little thicker than the other. Be careful with drawing broken lines. We typically don't like that type of thing. We really want to see smooth lines. So you can make one darker than the other, but you can label them right on the curves, and that makes it a lot better. Graphical analysis. Now we're using graphs. So typically we either use slope or area. And then sometimes you'll even use the intercept. So whenever you calculate a slope, make sure that you always use points from the best fit line. Don't take points from the data table unless they pass through that line, okay? If the graph is unfamiliar, look at the units, and then that will usually help you kind of figure out what physical quantity you're looking at for the slope. And if you do have a graph or set of data and they give it to you, watch out. Look out for outliers. They like to put those in. Data points that are a lot off, ignore those. We don't want bad data points. So we've got to get rid of those guys. Okay, the most common slopes. Position versus time. If you have a position versus time graph, that's velocity. Velocity time graph is acceleration. And a force elongation or a force stretch or force compression graph gives us the spring constant. The most common areas under the curve include velocity time, that gives displacement, acceleration time, which gives change in velocity. We've already been through force time, which gives us impulse, and force distance, which gives us work. Hopefully you're seeing why earlier we spent most of our time with energy, momentum, and simple harmonic motion. Mainly we did momentum because of this, and we did energy because of this one. So that's where these things start to really come together a little bit better. All right, you've all drawn free body diagrams. You know you always want to use a ruler to do this. They need to be straight arrows. They need to have a tip on them so we know which direction they point. And you always want to start them on the center of the dot. If you don't start them on the center of the dot, it's really difficult to give you points because you're not really associating with that arrow with anything. Don't draw components. So remember, just draw the forces. Don't draw mg sine of the angle and mg cosine of the angle. That's bad. You can do that somewhere else, but not on the free body diagram. If you have something that's rotating, they're going to want you to draw everything from where that force starts. So we've got an example of that for later. We will show you and label your forces. If FG is great, MG is better, W is okay, FN is great, you can use N, FF is fine. Little f for friction is okay. This is probably better. Tension, FT or T. Force of a spring, always do FS. If you just put S, that might not work. You're going to want to use the force of a spring. So those are important things. Never write FC on a free body diagram. Always write down what the actual force is. It's usually tension or normal force. If there's two forces in the same direction, draw two arrows. Don't draw one arrow on top of the other. They need to be side by side. If you need to, make the dot bigger. That's what we always tell everybody. Write net force for the coordinate axis for each coordinate axis, and always write what that net force is equal to. So it's either 0 or MA or MV squared over R. All right, let's talk about paragraph length response. So there's some things that we've noticed over the years when we grade these, and probably the biggest thing is a lot of you like to use claim, evidence, and reasoning, and that's awesome. I think that's one really good way to do it. But when you do it, you absolutely need to be careful because your claim is usually your answer. Your evidence, you've cited evidence, and your reasoning really needs to include what we call basic physics. I've got a different way for you to do this, and I think you'll get more points if you use it. This is called the BCDA. So it's like ABCD, but we're going to put the A at the end. The B stands for basic physics, basic principles, or basic equations. It's really when you talk about physics. And I want you to do this first on your exam if you use this, because if you talk about the physics first, you've hit what we really want. We want to see you understand the physics that goes with the equation, or with the question. So state of principle of physics, the law of physics, or physics equation that's relevant to the situation. So if it's about work and you're putting momentum, that's not the same. So be really careful. So there's a lot of different ways you can do this. You could set some equations, and that would apply for something moving with constant velocity. It could be v is equal to d over t, d is equal to v times t, or t is equal to d over v. Any of those would work. Velocity equals distance over time, or time is equal to distance velocity. You could say them. A physics principle that says the same thing might be time and speed are inversely proportional, or going faster results in less time of travel. Stating important definitions also counts for basic physics. So if you say if an object has more mass, it's more difficult to make the object reach a certain speed because it has more inertia. Kind of like saying an impatient person wants things to take less time. Cite evidence. So in claim evidence reasoning, this is your evidence part. You need to really show, if they give you a diagram or a picture or a graph, make sure that you talk about those things. They've put them there for a reason. If you're presented with a couple of different cases, so maybe two objects, two different things, compare them, contrast them, because they want you to do that. So if they have two different scenarios, compare and contrast them. The second to last thing to do is draw it together. So now you've got your base of physics and your specifics of the situation. Show how they come together. And then once you do that, answer it. Answer the question. This is where a lot of people don't do it. And we always go, answer the stinking question, because a lot of you forget. You give us a great response, but you forget to answer the question. So if it says which item is going faster, make sure you tell us. You can talk about physics of each one. You could give us the speeds, but not answer the question and miss a point because you didn't tell us which one was faster, which one was slower. So be really careful that you do that, because that is super important. All right. In some cases, there's really no answer because they've given you an answer. So you really just have to do steps B, C, and D. So just kind of be careful with that. All right, here we go. We're going to practice. A student drops a bouncy ball from 1 meter height, and the ball bounces up to the 0.8 meter mark. In a clear, coherent paragraph length response that may also contain figures and or equations, explain why the ball doesn't return to its original height. All I want you to do on this is just talk about the basic physics. You can use an equation. You can use a bunch of equations. You can use a description. But remember, 99% of the time, when you start your basic physics, it's either Newton's second law, the net force is equal to mass times acceleration, conservation of energy, or conservation of momentum. So using this one, think about which one you would want to use and then just state it. That's all you have to do. You don't really have to do anything else. So here, just talk about what you're going to use. You want to either say, you want to use your basic physics in terms of energy, in terms of momentum, or think about Newton's second law, where you have F equals ma. There's one probably that's a lot easier to do than any of the others. Beautiful job. Oh, you guys are doing great. I love it. Ah, awesome. Yeah, beautiful answers. So Sarah has an excellent answer here. Good job, Sarah. Keep going. You're doing great. So I'm seeing a lot of people are going through and they're giving me beautiful physics here. Most people are talking or typing about conservation of energy. So if you think about it, when the ball's up high at that 1 meter height and it's not moving yet, it's got all potential energy. When it hits the ground, when it gets to the ground, I guess, it has kinetic. And then when it bounces back up to the 0.8 meter mark, it's back to potential again. So some of you have also included some other things here. And you've done a great job with it. So nice job. So here's kind of what I said. I went in and just said the following. So let's see if we can get this to come up. Oops. It actually went on. So I'm going to back it up here. Again, doink. Sorry about this. It's getting confused between going from one to the other. All right, so my basic physics would say conservation of energy applies in this situation because we're starting with potential energy due to gravity, and then we're moving on to kinetic energy at the bottom, and then there is some work done. When it hits the ground, it makes a sound and it loses energy, kinetic energy. So when it gets to the top, it can only go to the 0.8 meter mark. So that's my basic physics. When I cite evidence, what would you cite here? So what would you say? So if I want to cite evidence, what did the ball do that kind of shows that it did lose a little bit of energy? So how do we know that it lost some energy? Oh, yeah. I like what you're doing. Ah, see, this is beautiful. So now I see a lot of people stating that when the ball hits the ground, then the ball is losing energy. And it's losing it due to sound or some sort of deformation. So the ball gets squished a little bit. And then it comes back up, but it only goes to 0.8 meters because it lost some energy there. Beautiful job. All right, so let's go ahead. We're going to go from cite evidence to draw together. When you draw together now, and I know it feels like you're just saying the same thing over and over again, and that's okay. So here, you'll probably go in and you're going to start something with, kind of think about, what did you say about basic physics? What did you say about your cite evidence? Paraphrase that, make it smaller. Usually with this part, you can start with therefore. You can say therefore, or you can say since energy was lost, and we started with potential energy at the top, converted to kinetic energy, which then got lost and comes back up. That's why the ball only bounces up to 0.8 meters, was energy was not conserved. Mechanical energy wasn't conserved. All righty, so let's go ahead and let's move to the experimental design questions. So when we do the paragraph length response, I know I always have my students use the BCDA method. You can also use claim, evidence, and reasoning. So that's what the College Board usually has their answers in. When we do experimental design, we've got a different acronym to use. So I like to call this one D square. And you'll notice the only letter when I spell D square, the only letter that's lowercase is U. And that's because the acronym stands for diagram, setup, quantities, apparatus, repeated independent variable, and then the last one is error reduction. So we're going to do each one of these, but we're going to actually also answer a question doing this. So if you do this on tomorrow's test or on the 24th, and you use these letters to kind of help you, you're going to have a much better answer than most of the other students in the room. And it's because you have a plan. So even when you sit down to take an English test and they want you to write, a lot of schools have some sort of acronym that you follow. So sometimes it's axes, sometimes it's PEEL. There's a lot of different things that you can use to write effectively. So for physics, experimental design questions, if you remember D square, you'll do really well. So here's the question. How could you find the spring constant for one of these jumping toys? And the jumping toys work like this. You'll notice there's a little suction cup at the bottom, right below the head. When you press this down, it's going to look like the blue guy. So the blue guy is loaded. He's ready to go. When you squish him together, there's a little bit of suction there, but it slowly releases until the spring pops. He pops up in the air and then comes back down. So that's kind of how they work. I could not find a video of these things in action. I need to take a video of this. They want us to go through and explain how we could find the spring value in an experiment. So the first thing that we're going to do is draw a diagram with labels. You want to draw a diagram that includes any equipment that you're going to use, as well as the object. But you don't need anything else. You don't need the earth. You don't need to draw your teacher. You don't need to draw all your friends. You don't need to be Picasso either. You don't have to be Michelangelo. You can draw stick figures. I always tell my students, kindergarten pictures. That's the way to do it. Make it super easy. Draw everything a stick figure or a box. So if you need a balance or a scale that you would plug into the wall to find the mass of something, you can do that here. Draw a box and then next to it, write scale or balance. When you draw the toy, a little curly Q with a box on top is awesome because that's all you need. It does not need to look like the dragons or the multi-eye guy here or the single eye guy here or this guy. It doesn't have to look like any of the aliens that you see there. It can be just super simple. So make things super simple. I'm going to give you a couple minutes to draw what you think you want to draw for this. Remember, you're really drawing the object and any equipment that you would use to measure things with. So think about what you would measure. Beautiful pictures. You guys are doing great. I love it. Yeah, very nice. Label all the objects. I thought somebody wrote banana. They didn't. They wrote balance. Nice. Very good. Yeah, and they don't have to look like it either. As long as it's a picture and you try your best, that works out really well. Very nice job. I love it. And there's a couple ways to do this. So if you don't do it the way somebody else does, that's absolutely fine. I love your pictures. They're beautiful. Good, good, good. Excellent pictures. Love the labels. Nobody's trying to draw anything super detailed. The big thing you want to do on these is keep everything simple. Somebody had said, Kiss, keep it simple, student, because the more simple it is, the more time you can spend on really explaining what you're doing. I think that's the important part. Beautiful job. Okay, so I've drawn a picture too. I want to show you what my picture looks like. This is my picture. Like we said, just draw a little head on top of the spring. I drew a table just for fun. I put in my great big ruler meter stick. Here's my balance. I used a motion detector too. You wouldn't have to use the motion detector if you have a ruler meter stick. You wouldn't need a ruler meter stick if you had the motion detector. Although you might need this. Yeah, you would need it because you have to measure the compression of the spring. So I've drawn everything I need. And now I want to do the next part. So remember our question, how could you find the spring constant value for a jumping toy using conservation of energy? So if you're trying to use a Hooke's law apparatus, that wouldn't work because we're trying to do conservation of energy. So here we go. The next part is the S, Q, U, and A. And we do these together. Why do we do these together? We do these together because they go together. So your setup is going to explain anything that your diagram doesn't clearly show. If you think about the diagrams that we've all drawn, and they're beautiful, you guys have done a beautiful job on those. This doesn't tell that I have to compress the spring. It's a great picture, but it doesn't tell that I have to compress the spring and measure the compression. It doesn't tell that I have to let go of it and then either measure the speed when it's completely done, uncompressing, I guess, and find the speed then, or find the height that it goes. So it doesn't say that. And those are things that I need to say. But when I do that, I need to tell what quantities I'm going to measure and what apparatus. And I know that they're listed here, but we still have to tell what we're measuring and what thing we're measuring it with. So we're going to go to the next part. If you are going to do this using speed, so you're using kinetic energy, this is probably an equation that you would, if you remember, we did this earlier. Remember, we solved for the spring constant, and we did it using the kinetic energy, and we said that the spring energy was going to kinetic. So there that is again. This one is for if you're using potential energy. Don't do both sides. Pick the side that you think your picture best matches with. Make it super simple. You're just going to say, what are you going to do? What are you going to measure? And what are you going to measure it with? And remember, you're measuring two things. So think about the two things you're going to measure. Think about what you're going to use to measure it. I'm already seeing some awesome ways that you guys are doing it. So Michelle's doing a good job here. Nice job, Noah. So you want to go through here. We're telling what are we measuring? What are we measuring it with? And then what basic thing are we doing to get this experiment moving? So most of the time things are going to move in physics. So tell me, how are you going to get this spring to jump? So what do we have to do? So what are we going to measure and what are we going to measure it with? You guys are doing fantastic. A lot of you I know are asking about Gimkit. Here's what I want you to do. Go to your teacher tomorrow, ask them to go to the Gimkit site, and they can demo it. And you all can play. Now, not tomorrow if you're taking the exam, but if you're not taking the exam till the 24th, show your teacher Gimkit. I think that's the best way to do it. Show them Gimkit. Tell them that they can search for question banks that deal with AP Physics 1 questions like what we've been doing. They can set that up and you all can play in class. Or if you're virtual, you can do it online just like we did. So that's the best way to do it. One thing I can do is I will go in and I will find a way to print those questions. I just finally read correctly some of the questions that are coming up. I will go in and I'll print those out, and then we'll get them in the site. So I will get with somebody and we will get that done. All right, cool. All right, you guys did a good job on this. I like it. And I love the fact that you are telling what you're measuring and what you're using to measure it. Good job. So I went ahead and did both sides. And so I'll show you my answers for both sides here. I'm going to back it up one. So if I was doing the one on the left, I would say measure the mass. Oops, sorry. I'm going to have to go back up again here. Measure the mass of the toy with the balance. Compress the toy on the table and measure the compression with the meter stick. So see, I'm doing both setup and quantities. And thirdly, I'm also doing the apparatus. So compress the toy is my setup. Quantity to measure is the compression. And the apparatus to use is the meter stick. So we're doing that over and over again. Let go of the toy, and when it rises, record the velocity of the toy using the motion detector. On the other side, remember, we're measuring it as how high it goes. So for this one, I say measure the mass of the toy with the balance, compress the toy on the table, and measure the compression. So I'm doing the same thing again, but now I'm going to measure the height that it goes. And if I want to be more precise, so I'm trying to get rid of error here, I'm going to use a cell phone slow motion camera to better see how high it goes. All right, you guys did great on that one. Let's do this next one. The next two layers or letters that we have here, are the layers of the question, are repeating the independent variables. So we need to say how the trials are to be repeated. So what quantity am I going to change? And what is it that I don't change? So I might say something like, for 5 trials, increase the height of the top of the ramp on each trial, but keep the length of the ramp the same. When I do error reduction, the best thing to do, if you can do it, if it's applicable, is to say, do each run 3 trials and average. So if I compress the spring 3 centimeters, I'm going to do that 3 times, and then I'm going to average the height that it goes each time. I'm going to just go through, do it 3 times. I'm going to get 3 different heights. I'm going to average those. So that's what you really want to do. If you can do those things, you're going to score super well. Remember, this is a 12-point question. You want to get as many points as possible. Let's do the same thing. So now, what is it that you're going to repeat? So what is your independent variable? So if you did the speed, you want to do that on the left. On the right, you're going to do, remember, you're thinking about what happens to the height. I think for both of these, your independent variable is exactly the same. So think about, what is it that you would change? What's the easiest thing to change, the one that's going to relate the most? It's typically what's on your x-axis of a graph. So if k is your slope, then x squared would be on your x-axis, and mv squared would be on your y-axis. On the other equation, 2mg delta y would be on your y-axis, and x squared would be on your x-axis again. So we want to think about, what is it that's easy to change? The mass might not be the easiest thing to change, but what are we going to vary? The easiest thing to vary would be, and a lot of you are putting it, the compression. So you're changing the compression each time. Good job. So when you change that compression, you also would want to tell by how much. Right now, we don't need to do that. And then what is it you're going to measure? So that's going to be different for each side. And when you measure it, then just make sure that you're going to repeat the process several times. And that when you repeat that process, you will do a good job of making sure that you average your 3 times. All right, you guys got it. I'm looking at your responses. I'm super happy with those. Here's what I said: repeat the steps, but increase the compression each time. Did that on both sides. And I also said for each run, do 3 trials and average the data. Now, I need to be more specific. I need to say average the speed on the left, and on the right, I want to average the heights. But that's really it. So nice job on that, okay? I think the next few things are things that I'm going to kind of show you here, since we're running out of time for this session. We still have about 10 minutes. I have Bendy Straw and Annabelle. Sorry about the puns there. They're trying to determine the acceleration of a toy car. We're going to assume that they have all the equipment commonly used in a physics lab. Explain a procedure in which they might find the acceleration of the toy car. All right, it is your time to shine. I want you to draw a really basic diagram. Don't forget about the toy car. And then just put in the things that you're going to use to measure. You don't need to put in anything else. Then I want you to do your SQUA, and then we'll stop. We'll take a look, just make sure that you feel good about your answers. And then we'll move on to the R and the E. And we're going to talk about how we would analyze this one. So we'll give you a little bit of time here. We still have about 9 minutes before we take our last break of the evening, believe it or not. I love your pictures, and I love the different ways you're doing this. Beautiful job. Excellent job. You can use anything that you would find in your lab. So some of you are using photo gates, so you could do that. Some of you are using just stopwatches and meter sticks, and that's okay too, because you can do it with those things. I love some people are using force probes, so that's really awesome too. Motion detector, there you go. That motion detector will save your life when you take the test, because you can use a motion detector to do a lot of different things. I love it. Good job. Whatever you do, make sure that if you put down an equipment item, you do mention that you're going to use it. They really want to make sure you do that. Remember, your pictures can just be stick figures. They don't ever have to be super great. Now, if you take the AP art exam, I'm sure you're going to have to do some things like that, but usually there's a portfolio. Excellent. I'm looking at these pictures, look good. And then a lot of you are putting into the SQUA. You're telling me what you're measuring. You're telling me how you're getting the car to move. So remember, if you're using a ramp, that's one way to do it. If you have a car that has a spring inside, so we call these pullback cars, you might have used those. Some of you might have used fan carts, where there's a fan on the cart and you turn the fan on and it makes it go. Some of you have like the old toy cars that you put a kind of a stick in, not a stick. It's like a little thing that has little teeth on it. You pull on it, it goes like that, and then the car takes off. So that's fun too. So any of those would work. Beautiful job. So I see lots of great pictures. Don't forget the SQUA. What are you going to do to get it moving? Good job. I love it. Good job, Eduardo. Mashed potatoes. Somebody calls themselves mashed potatoes. I like it. Ashley, good job. Caroline, good. All right. Fantastic. Let me show you what I did. See if it compares to what you did. I think it will. So let's get this guy to move. Come on, you can move. Oh, I went too far. Okay, so for this one, what I would do is I would just say I'm going to use a motion detector and I'm going to use a pullback car. That's all I need. I'm going to measure the position versus time, the velocity versus time, using the motion detector, and then I'm going to use those graphs. So now on the R and E, what is it I'm going to repeat? So I'm going to have it travel 10 centimeters. Then I'm going to have it travel 20. Then I'm going to go 30. Then I'm going to go 40. Then I'm going to go back and I'm going to plot that. And when I plot that, that should help me. Error analysis, just like we said before, we want to do this several times. I verbally just kind of talked about that a little bit because I think it's important that we kind of keep moving here because we're running out of time. So let's go to the graph. I want you on the graph, and so the graph should come up here for you in a second, I'm hoping. When the graph comes up, tell me what are you going to plot on each axis so we can find the acceleration of the car. So think about what you measured and what could you plot to help you get the acceleration of the car. It doesn't have to directly get you there. It just has to have some data on it that you can use to get you there. So hopefully here in a second, you'll be on that slide. Yeah, there we go. Okay, so now I think you should be on that slide. We'll see if it'll come up. And we'll definitely reset this when we come back because I think it's getting slow with all the people. So for this graph, just because we only got a minute left here, the things that you could think about doing is you could put the force on the y-axis and you could put the mass on the x-axis. Okay, so if you measure mass, if you didn't do that, we could do position and time, and then we could linearize. So don't forget, you can linearize things. So that is the other way to do it. So to find the acceleration, you know, there's a lot of different things to do, but mainly it's thinking about trying to linearize our graphs. And I think that's probably the best way to go about it. All right, we're going to take a little bit of a break here, and then we will spend a little time talking about multiple choice questions. I'll give you some tips and tricks. And I have a feeling that we have some people that might want to do Gimkit. So I have talked to the powers that be. We have some awesome people that work for Fiveable, and they do a great job of giving us some things that'll help us. I will tomorrow go through and print off the questions that have been on the Gimkits, and then we will attach those to the slides, and you'll be able to pull those tomorrow. So not enough time tonight to do that, but definitely we'll be able to do that tomorrow. So here we go. Last 5-minute break. You guys are awesome. I just want to tell you that. You guys have been doing a great job. We're going to do a little 5-minute break, and we will see you in 5. Alrighty, here we go. We're in our last hour. And it is time to move on to multiple choice. So multiple choice, be careful when you do multiple choice. Because when you do multiple choice, your tendency is to pick the answer that looks good. The College Board, the people who write these questions are really good at making answers that are totally wrong look really good. So please take your time on this part. But you have to move. Use a regular pencil. That's super important for this. Doesn't matter, but use a regular pencil. If you use a mechanical pencil, sometimes the mechanical pencils have lead that don't show up very well. So please, 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 okay, make sure you do that. Do use a calculator. So for the multiple choice part, you can use a calculator. You might not need it, but you probably will use this, your calculator more on this section than you will on the free response section, believe it or not. And you can also use our equation sheet. So don't forget, they should be, when you get your booklet, it will have this in it. Use it, okay? Use it, use it, use it. Make sure you do that. All right, cool. There are 50 multiple choice. 45 are what we call single response. So you really, really, really want to answer just one answer for those. Yes. There are 5 multiple response. So there are 2 answers there, okay? You have 9 minutes to complete the multiple choice. That's 1.8 minutes per question. More detailed, that one is 1 minute, 48 seconds, okay? But don't rush. Make sure you watch the clock. Some questions take a little longer. Some of them take a lot less. I did see somebody say in regards to the pencil, on the multiple choice, you have to use a pencil, okay? You really shouldn't use a pen. Because if you need to erase an answer, it's really hard to get pen off of the multiple choice. Now, on the free response, some places they want you to use a pen, okay? They want you to use a pen. I still think you should use a pencil, but that's going to be your personal choice. Pen shows up better on the free response, might be a little bit easier to read unless you make a mistake. Oh, one more thing, super important. On the free response part, if you make a mistake and you don't have time to erase, or if you can't erase it, draw a line through it. Whatever you draw a line through, we don't read. Whether it's right or wrong, we won't read it. So if you don't want something to be read, scratch it out, draw a line through it, and we won't read it. Okay, cool. Let's go ahead and take a look at this. Right on the multiple choice. You can, you should. Please make sure you do that, okay? Go through and do the questions you feel most comfortable first. Don't go in order unless you absolutely can't take it and you have to go in order. Please don't, though. Do the questions you really feel comfortable with first, okay? Mark off answers that you can eliminate. So if you get to a question you're not really sure, mark off as many answers as you can. Circle that question because that means you're going to go back to it. Once you go back to it, If it's a circled question, then cross off your circle. Help yourself. The other thing that I really encourage you to do when you do these is draw a picture. So if it says, there's a person standing at the top of a cliff, draw the cliff and the person, because it might be that there's something that drawing that picture might actually spark something in your brain. So do that. That's a really, really important. The questions that typically require a lot of time are the ones where they want you to pick the right equation, okay, or manipulate algebra into an equation. Sometimes they're easy, sometimes they're not. The other ones, believe it or not, that take a lot of time are ones where they want you to calculate an answer. And so they have many different number answers with units. Sometimes you can do those quickly, but most of the time it takes a little while to do. So you might circle those and go back to them. Do the things that are super, super quick. Read each one of the questions carefully, okay? Circle all the keywords. So if it says differentiate between, if it says anything like that, circle those words. Think of physics principles. So is this energy? No. Is it a collision? Ooh, must be momentum. Is the object moving in a circle? Oh, it's rotational motion or simple harmonic motion. If the answer looks really obvious, Mickey Mouse type, like it looks, oh yeah, it's got to be that. If it's too obvious, reread it again. The question might not be that simple. If you don't know an answer, eliminate incorrect answers. So that's probably the easiest thing to do. Proportional reasoning, so that is where you use equations. So if you have F equals MA, we talked about this before. If M stays the same and A goes up, F has to go up. Do that instead of plug and chug, okay? Watch out for the last 5 questions. Make sure you pick 2, make sure you bubble 2 in. The last thing that I really want to make sure you understand is don't leave any question blank. There is really no penalty for guessing. So if you are really running out of time and you need to get something, go in and make an educated guess, okay? That is the best thing to do. And that will help out big time. So I think that's the cool part. All righty, next thing that we need to do is let's go through just a few multiple choice questions together, and then we're going to have a little Gimkit battle, and we'll see how we do on Gimkit. This is our first question. Go ahead and read the question and answer. I'm going to give you just a little over a minute and a half. Go. Once you have the right answer, you'll want to drag your red dot on top of the letter. So it's kind of like bubbling it in. That's what I was hoping for. This one has a little bit of math to it, but it should be pretty easy to do. Our 2 most popular answers so far in this one are B and C. Nobody has picked A or D. So we've got a choice to make. All right, here we go. Let's take a look. And the correct answer for this one is definitely C. So this one is C. Good job. Excellent. Let's move to the next one. Here we've got an object attached. Notice there's no math on this one. An object attached to one end of a string moves in a circle at a constant speed. Which of the following is correct? So this is one that should not take that entire 1 minute and 48 seconds. This one should take you probably less than 30 seconds. Seeing a lot of correct answers here. All right. Good job. Okay, so for this one, the object is accelerating. So even though it's moving at a constant speed, it's changing directions. And because it's changing directions, it is accelerating. Its velocity is not the same as its speed. It does require force. And if the string breaks, it will not go in a circle. It will take off at a straight line. Good job. Yeah, hey, keep helping each other. I love the fact that you're going in on these. And if you're not sure why the answer is the way it is, if somebody else can explain it in Discord or in the chat, that's awesome. Good. You guys got this. How does an air mattress protect a stunt person landing on the ground after a stunt? So remember, cross off ones in your brain that you know are not right, and then pick the one that you didn't cross off. You guys are doing fantastic. I love how quickly you're doing this one. Good. We talked about this earlier. I think that's the cool part of being here tonight. Hopefully, like some of the things we've talked about, when they're on the test tomorrow, you'll fly right through those. That's our hope. That'll give you more time to do the more difficult things. Yeah, so most of you have answered this one correctly. It lengthens that stopping time. Good, perfect. Excellent job. All righty, here we go. Next question. This is another one that says, were you paying attention tonight? Were you here earlier? Oh, shoot. Let's go. There we go. This likes to go back and forth on us, doesn't it? Yeah. So just like it was earlier, this one is definitely F times delta T. Good job. All right. So let's do one that is rotating. Let's do one that is rotating. So now we've got a child rotating here. There we go. On a platform. So here we go. This one, rotational motion. So go through, think about ones that can't be right, and then try to find the one that is. So which one is going to increase the speed of the platform child system? Seeing some good answers here. It looks like you guys have the right one. So this one, definitely letter B. So when you move towards the center, you decrease the rotational inertia and it should pick up speed. It's very similar to if you sit in a chair that can turn and then pull your arms in, you'll go faster. Pull your arms out, you go slower. So same type of thing. Don't forget, there are certain topics some of you might not have been through. So if you haven't been through some of these, remember there's a lot of questions. And so some of the questions are ones that don't deal with this. So here we go. Next question. So this one, you've done this before. Let's see if we get this one. So we have a railroad car, mass M, moving along with speed V, collides, connects to a second railroad car. So think about the type of collision for this one. And then think about the kinetic energy and then work backwards to speed. So this one is kind of tough sometimes because lots of people want to do the speed first. I think you can do the kinetic energy first. And then that will help you with speed. All right, that looks really good. Oops, went too far. So this one is definitely letter A. So we did that earlier. Let's go ahead and do this now. This is a new one. So this is one you have not seen. Okay, so here we have both a spring system and a pendulum. And we have an oscillating spring system and we have a pendulum. Oops. And it wants us on this one to, there we go. This one wants to know what is true for both spheres. So they're undergoing simple harmonic motion. I don't know why that keeps moving back and forth. It's late. That's what it is. What is true for both spheres? So we're looking at some energy here. Yeah, you guys are doing good on these. You're doing really well. So this one is letter A. So the maximum kinetic energy is when the sphere passes through equilibrium. And so they showed you equilibrium in both. So that should have been a little bit of a hint. Okay, so let's go to the next question here. We have the figure above showing forces exerted on a block that is sliding on a horizontal surface. So this is one where you absolutely have to read what's going on. It is sliding on a surface, okay? They want to know what is the acceleration of the block. They do give you the coefficient of friction. They give you gravity and the normal force. Notice they're equal and opposite. So it's not lifting up. It's not going down. Doing a beautiful job. Good. Nice job. So remember, the force of friction is equal to mu times the normal force, and you've got both those. And you know that the force of gravity is equal to the mass times gravity, and you know gravity and you know the force. So you should be able to find the mass. Then from those, you can find that acceleration. So this one, your answer should be 2 meters per second squared, and it is to the left. So we definitely want to make sure that one's to the left. Cool. All right, here we go. Let's go to the next question. So This one's a little different. You're going to notice that it does have a graph on it. You're going to see a couple of questions that will have the same graph, but will be a different question. You have a cart. It is moving along a straight line. So please notice this one is not a position versus time graph. We have a varying net force along the direction of motion. So it's either getting pushed or pulled. The cart's velocity as a function of time is shown in the graph. Read the description because I think that'll help. And then there's 4 sections: A to B, B to C, C to D, and D to E. During some part of motion, the work done on the cart is negative. What feature of the motion indicates this? I'm seeing a lot of good answers here. All right. And this one is letter B. The speed is decreasing. Be careful. Okay, so we do know the acceleration is negative from C to D and from D to E. So that one would be kind of tough to answer. So the speed is decreasing. So that's the best one. All right, here we go. Next question. I've got a couple of solid spheres. They both have the same radius. They're both made of the same type of steel. They're placed in contact. The magnitude of the gravitational force they exert on each other is F1. When 2 other solid spheres of radius 3r are made of this steel, what is the gravitational force? So they'll do this to you a lot. They will take a couple of objects, they will change something about both objects, and then they will ask you about the gravitational force. And I saw a lot of good answers. Look like you guys had kind of the same thing. So remember, radius, both of them changed. They went from R to 3R. So they both went up by 3. And if you think about the equation for 2 objects, the gravitational force, remember, that's big G is equal to M1, M2 over R squared. And so if you do that, if we take 3 and we square it, we get 9, and each one is 9. So your answer should be 81 times the force. That one's tough. That one's a hard question. That is not easy. That relationship was a little bit more difficult. Alrighty, let's go on and take a look at the next one. Oops, skip back on me. I didn't want it to. So let's go to this one. It likes to do this, doesn't it? All right, here we go. Come on back. You can do it. So you know what? Come on now. All right, if it doesn't stop, we will stop it and we'll move on. All right, so we're just going to stop this one. So I'm going to end this guide. Let's go back. We will do Gimkit for a while, and then we'll come back when this thing wants to behave. And we'll do that. All right, so, okay, so I'm going to end the pair deck, and let's go in and let's do, we're going to end this session. We'll go back into it. Let's go back into Gimkit. And let us go in and let's do, I actually have a big one here that does a whole bunch. Okay, so this one is over several different sections. So we're actually going to play this one for about 25 minutes. I bet 25 minutes. We're going to do this one for about 15 minutes, okay? So we will move this over. We're going to do classic. We're going to do 15 minutes for this one. It has lots of questions in it. which should be super helpful. And here is the code 12582. I'm going to put a link into, give one to Brianna if she's still around. And then we will put it into, there we go. So now the link is both in Discord, and I think Brianna has it, and then you can see it here too. So you guys go ahead, hop on there. I'm also going to hop on. And we will all play for 15 minutes. And then we'll go back and see if the Pear Deck will allow us to do a few more of those together. I'm glad to see you guys are still here. This is awesome. You're doing a great job. I really, really appreciate you guys coming out. This is your dedication to doing well on the exam. That's what we love. Love to see you guys work. Love it. Beautiful job. All righty. We will keep this in the chat. I put it in Discord too in that chat, so you should see it in the physics section. And here we go. All right, you guys are doing great. Oh, that's weird. Oh, that one's weird. Oh, yeah. There we go. Somebody change the music. Good job. I like it. Thank you for changing the music. Oops. All right, got a little less, about 9 minutes now. About 9 minutes. You guys are doing great. Change the music again. Thank you. Nice. Oh, this one's tough. 4 minutes, 30 seconds. 4 minutes, 30 seconds. Here comes the music again. Job. We've got about 2 minutes left. 2 minutes. The summer music is possible. I love the summer music. One minute. You have 1 minute. 10 seconds. All right, here we go. And our winners, Kritika, Alexander, and H. All right, cool. So here's what we're going to do. We still have just a few more multiple choice questions to go in the Pear Deck. So what we'll do is we'll go ahead and move that back onto the screen. We will get you to log in. Here is the code again, RTBBIK. RTBBIK. You know, it's late when I'm starting to sing. RTBBIK. So we'll put that in here and see if you can get in. I'll put it in Discord. So we still have about 19 minutes left. We'll do a few more of these. I want to talk about friction just a little bit. And then we'll see what time it is. We've got about 19 minutes left. You guys are doing fantastic logging back on. I appreciate what you're doing. Thank you so much. Oh, wow, that's cool. So I'm watching Discord. Some people have the test pretty soon. They're in Asia, and it is in, looks like 3 hours. You'll do great. You all will do awesome. All righty. So it looks like we're kind of leveling out there a little bit. So we're going to go ahead and continue. Hopefully this behaves for us. So while traveling in its elliptical orbit around the sun, Mars gains speed during the part of the orbit when it's close to the sun. Which of the following can be used to explain this gain in speed? So we will give you 30 seconds. Here we go. Ten seconds. All right, good job. Here we go. Here's our answer. It is letter A. The sun system, Mars system, loses potential energy and Mars gains kinetic energy. So it does go faster. Excellent. Here we go. Next question. 2 blocks, masses M and 2M initially at rest, and they're on a horizontal frictionless surface. The force F is exerted on each block, and it says shown above, but it's to the right. The graph, how F varies with time. T, which block has the greatest average power provided to it between 0 seconds and 3 seconds. So is that the block of mass M, 2M, both have the same power, or it can't be determined unless you know the ratio of maximum force to M. Pear Deck code is RTBBIK. So here we go. We'll put it in the chat. RTBBIK. Good job, guys. Sorry, I meant to put the code in there too. I forgot. So there's the whole thing. Sorry about that. All right. Good. Excellent. Excellent. Good. So this one is definitely the block of mass M. So notice that the force is 5, so it's got to be bigger on M because it has the smaller mass. All righty. Oh, I like this one. This is a good one. So we've got a couple blocks, block 1 and block 2. And we've seen this one before, but it was a different question. So obviously they collide they do stick together. They do stick together. And when they stick together, they travel the same speed. So they want to know, how does the kinetic energy of the two-block system after the collision compare to the kinetic energy before the collision? It was block A because it had a smaller mass, and we had the same force acting on it. All right, good job. Excellent. All right, looks like most of you have the right answer. It is letter A. Remember, they do have the same velocity, so they transform that kinetic energy into internal energy. So they might heat it up a little bit. All right, looks like the same question. So you're going to see these. They typically have the same, they have the same prompt, but they have a different question. So make sure you always do this, okay? So which one has a greater mass, and what information indicates this? So take a good look at what happened to each one. So they want to know which one has got a greater mass, and what information indicates that it has a greater mass. You guys are doing awesome still. Keep it up. 13 minutes. All right, cool. Looks good. Awesome. Yeah, block 2, because that final velocity is closer to the initial velocity. So notice that block 2 only changes 2 meters per second, but block 1 changes 3. The bigger one they are, the less it is. Good. Good luck, everybody. All right, here we go. Let's take a look at the next one. Again, same prompt, okay? Different question. So you'll see this on the exam. You'll see things like this. You won't see this question, but you'll see things like this. Which of the following is true about the motion of the center of mass? This is something that they really get you on, so you got to be really careful. Really careful. So they want to know what is true of the motion of the center of mass of the two-block system. You guys are doing beautiful. Keep going. Good, good, good. Excellent. All right, cool. Let's check this one. I'll give you about 5 more seconds. 4, 3, 2, 1. Yes. The center of mass moves at a constant velocity of 1 positive meter per second because there's no friction acting on the system. So the center of mass velocity, that one is a little bit tougher to do. There's an equation for it if you really want to know what it is. If you Google it, it'll come up and you can see it. So that is the way to do that one. All right, here we go. Oh, I like this one. This one's really good. So if you think you know what you're doing and you're on the track for a 5, this one should be okay. Shouldn't be too bad. It is a little bit tougher. So we have the position time, velocity time, acceleration time for an object. It is a marble. It is moving in one dimension. So they want to know which of the following could describe the motion of the marble. So by one dimension, they meant it's not like spinning or anything like that. It's not trying to move in a bunch of different dimensions. And I think the best thing to look at for this one is the position versus time graph. That one will help you a little bit. And it's interesting because it's kind of the opposite of a projectile. So this one, if you think of it as the opposite of a projectile, because most of you know what a projectile graph should look like, this one is kind of the opposite of that. All right, good answers here. It is rolling up a ramp and then rolling back down. So that's kind of cool. A lot of people like to pick this bowl thing, but if it's doing that, it's really not, it's going to have a negative acceleration. So be careful with that one. Good. Okay, here we go. An object is moving in a positive x direction while a net force directed along the x-axis is exerted on the object. The figure above, so that's really the picture that you see below, is a force as a function of position. What is the net work done over the distance shown? So remember what work is equal to. Remember we said it's change in energy, or it is F parallel to distance, or it is FD cosine of the angle. So if you do that, that should help you a little bit. All right. So remember, force times distance. So if I find the area here, and then I notice this area is positive, but this one is the same but negative, this area and this one cancel. So when you do this one, your answer should just be FO times D, because we're just multiplying to find the area of that square. Good job. Cool. Next one. Oh, I like this one. So a moon is an elliptical orbit, and you'll notice pictures down at the bottom because this is an old AP question. As the moon has a speed, and that's really velocity. I know they did it funky, but that's okay. Is at a distance RA from the planet B. At point B, the moon has a speed of UB. Which of the following explains the correct method for determining the distance of the moon from the planet at point B in terms of the given quantity? So what would you use? This one's either conservation of angular momentum or conservation of energy. So which one would be better? And then you'll have to check the last part of the answer. Yeah, there's always one experimental design question. And you're right. If you just go to the website that somebody listed, you'll see it. All right, good. Got some good answers here. All right, cool. Yep. So this one's conservation of angular momentum, and it's not energy. So we're doing that because that gravitational force exerted on the moon is always directed towards the planet. So that force is always coming towards the planet. Okay. Excellent job. Here we go. Next one. Just got a few more here. A cart is constrained, which means that it is made to move along a straight line. There's a varying net force. We want to know from which segment does the cart move the greatest distance? A to B, B to C, C to D, or D to E? This will be the last one we do. So the rest of this presentation is linked. And so when you go in, you'll be able to see it. I've got a few more tips really quick that I want to make sure you all have. Before you go. So we'll give you about 10 more seconds on this one. All right, this one is definitely A to B. It has the biggest area. The rest of them have a smaller area. So A to B, even though you have this curve here, you still have many boxes. You can kind of count the number of boxes. So you see not as many, very few, very, very, very few. So that's what it is. All right, guys. Hey, we only have about 4 minutes left. I want to tell you a couple things. I've been watching the Discord chat. Get some sleep. So if you are in an area of the world where it's already morning, good luck. You'll do 100% awesome, guarantee it. If you are here in the United States, you need to go to bed soon, get some sleep, okay? And first and foremost, don't worry about this exam, okay? Do the best you can. You're going to feel much better if you get some sleep, you go in, and you just do what you can, because that's the way this rolls, okay? So please, 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 please do that, okay? Read the questions, take your time. Remember what we said about a lot of these things is it's just going down and just really answering the questions and doing those things, okay? One thing I can tell you is there's some awesome things going on in the chat. I've been watching it. You guys are awesome to each other. I mean, I love the way that you guys have developed a really strong way of just kind of encouraging each other. So definitely go to the chat there, kind of look at the forums, go in, talk to other people. Everybody's stressed. Everybody's nervous. But you know what? In the end, if you're taking it tomorrow, it'll be over soon. And you can relax. And so do those things. Thank you so much for coming out and spending 5 hours. If you were here for 20 minutes, I love it. If you were here for the whole 5 hours, I love it. You guys were awesome. Make sure you do a big shout out to Brianna for being here tonight. She has done an amazing job this entire year. She has done a great job. No matter what you think you probably know a lot more than what you actually do. So please, please, please understand it's just a test. It doesn't define you. Okay. It doesn't say who you are. This is just a test. Okay. Not a big deal. So you guys will rock it. I'm going to watch Discord a little bit. If you have a few questions, we can answer those here in the following minutes. But you guys have done an awesome job. Please, please, please shout out to Brianna. She has just poured her heart out into this class and things that she does. She's definitely the GOAT and the legend and everything else on top. If you get a chance, thank Amanda. Thank everybody at Fiveable. They are doing an awesome job. Just really great. Peter's the other one that you can thank. He has done an absolutely beautiful job and has really, really helped people out. So please make sure you give those guys a shout out. Don't forget, everything is on the site. You'll have to go and grab stuff. Vimeo is where the video is. You guys are going to rock this test. So from Indianapolis, Indiana, tell you guys good luck. Have a great time. Get sleep. You're going to do better if you're not tired. Guarantee it. Okay? Just like driving or doing anything else, when you're tired, you don't do well. All right. Hey, thanks, guys. Have an awesome evening. Don't forget, come back, check it out. If you still are taking more AP tests, don't forget to check out the other stuff. You guys did an awesome job. Okay. So I think that is it. Last minute things. So for those of you that are still here, I can tell you that flipping physics site, it is the bomb. He is the GOAT. He does a great job. He's going to tell you good luck. If you're taking AP1, if you go to this AP Physics 1 review, he goes through everything, okay? If your test is in a few hours, don't worry about it. Not a big deal. But definitely, if you have time and you're not taking this until the 24th, take some time. Do a little bit of these, okay? He even took out the things that aren't on there anymore. So that's an excellent site. Another really good site to go to and do is Physics Classroom. So let me show you just one thing that I think is super helpful for my students. They're called concept builders. If you click on the concept builders and you go down to the topics, there are a ton of these. They even have them for chemistry. There are some things on here that you won't use unless you are in AP Physics 2. And you might see some things for AP Physics 2 or AP Physics C, E, and M. There might be a few things here that might help you a little bit. But these are super cool because you can go in and you'll notice like one-dimensional kinematics. You go in, you say Launch Concept Builder, it'll come up. And you can just be a guest. That's not a big deal. And then there's different levels. And so you can go in and they're going to ask you a question. You can type in the answer. If you say check answers, you don't get it right, it'll say Odrats, but that's okay. Because what it will do is it will allow you to go back and do another question very similar to it. So that is an awesome site to go to. That one is called thephysicsclassroom.com. And these are called the concept builders. And they are ones for almost everything. Not a lot for rotation, but for the others, there are some beautiful things there. Another site that you can go to is called physicsaviary.com. Physics Aviary. Oops. I'm going to have to type it in. Physics Aviary. And if you type that in and then go to the link, it's called the Physics Aviary. Sorry. And then in the homework section, they've got some awesome questions. So these questions deal with all kinds of different things. You'll see them for Physics 1, Physics 2, Physics C. Those will be on there too. There's an Atwood's problem. You can go in, you click on the problem. When it comes up, you say begin. It will tell you some information about this. You'll type your name in. You'll type in whatever they want you to do. So I'm just going to put that in. You'll say submit. And then it will run. And obviously I was wrong, but it'll tell you how long this takes to go. And then if you're really close, you'll know it and you'll be good. And I think you'll be set there. So the Flipping Physics site, here I'll put that, flippingphysics.com. That's where you want to go, flippingphysics.com, and that'll take you there. This is the Physics Aviary, and so I will definitely link this in the Discord chat. So Physics Aviary is there. The Physics 1 review, thank you so much. Sheet 12, that's perfect. So that's on there now. Yeah, you guys will be set. So you guys are good there. There's a lot of other things that you can kind of go through and just take a look at. Remember, AP Classroom, you can go in and you can watch the videos that are in there. So don't forget about AP Classroom. But other than that, that's it. Hey, thinking about you guys tomorrow. For those of you that are taking it, if you're taking it here soon and you're in Asia, good luck. Good luck to everybody else, and we will talk to you later.